and you're fresh to start. Is it possible to ask some, I want to see how many people have run the script that was shared yesterday. Let's say yes, yes on the chat. Okay, that is good. Are there any particular challenges that you think you face? The link for the Google link will be shared once more after we upload today's work on. I think Ellen has already done so, so the link will be shared shortly. So anybody who got any particular challenge? Yeah, the link has been shared by Ellen. You can copy the link, and you also can keep sharing along as we move on. Yeah. There was network problem. We didn't attend. I said also try to run the thing on running the script. Did you find any particular challenge? Okay, so I think we are going to start. The U-link will be shared shortly. Okay, so I'm going to probably take about 30 minutes to an hour to run these scripts. And then I'm going to hand you over to my colleagues, Dr. Ellen, to pick up from there. So the first thing that we need, the only package that we need for this session is Agricole. So I would expect the sound is not there. I think the sound should be there. Are you hearing me? Okay. Okay, that's fine. Okay. So how many people have installed Agricole? Can I see in the chat how many people have installed Agricole? Okay. So can I give a few minutes to save 2 minutes for those who have not installed to install the package Agricole? Just run the command here, open your script and run the command install packages Agricole. So 10:06, we're going to start. So I'm giving 2 minutes for people who have not installed to install. Install. So please remember, before you can run any program, you can do any data analysis in R, please ensure that you have the right packages. So the first thing that you need to do, you need to install the package using the simple commands, install.packages, and then you put in bracket the particular package that you are interested in doing. The installing of the package is only done once. So once you already have it on your computer, you don't need to install it again. Then the next thing that you need to do is before you do the analysis again, you need to load the particular package that you think you're going to use. So you use the function library, and then you should be able to load the package. How do I know that I don't have the package downloaded or I'm not installed the package? Once you try to run a particular command that belongs to that particular package, R will tell you this package is not found or this function is not found. So if once you see this function is not found, then you know that the package has not yet been installed. So you need to either go and install the package or you need to go and load the package. Okay, so let's now load the package Agricole. So we click on here and then we run. So on top of the console, there is a small sign, a red sign. If it is running, it tells you if the program is still running. You can also see here there is a small brush here for cleaning the console. So those who are looking for how to clean the console, there is a small brush here that you can use to clean the console. So if, for example, I click on this, it cleans my console, okay? So I have a small starting here. So the first thing that we already done with my two colleagues, the first thing is R works on objects. So you need to create an object. So for example, here we are going to create an object called reaction. And this object called reaction has only 4 observations. You have 10, 9.5, 11, and then 9. So as you can see from here, each object, each value in the object is going to be separated by a comma. So once you think you've written your command, your line correctly, you click on it and then you click on run. Some people yesterday were saying, well, run is not appearing. So for me, you could as well do this. You can actually copy this and paste it in your console. You can copy this and paste it in your console. So from here, you'll see that on this side, it looks like I have a number of things. I have a number of things already in my environment. You can see my environment. So the first thing I'm going to do, I'm going to remove everything in my environment. Okay, so you can see from here that my environment here is empty. So the first thing I'm going to do, I'm going to create an object called reaction. So you can see the first thing is that it is recorded in my global environment. Now I've created this object called reaction. So I can actually find out what this object is. I can just type the name here, reaction, and run. And then it will show you, it shows you the different, so here you can see the first one is 10, the second one is 9.5, 11, and then 9. So as we saw on the first day, you can also just get a particular elements within your object. In this case, our object is a vector. So what I can do is if I want to get the first value, I want to get the first observation, I just type the name of my object, and then in the square bracket, I put the position that I want to see. So if I click on this, it will tell me the first object is 10. Okay, so we can run this as mean. So what it does, it picks my object, and then it uses the function mean to calculate the mean. We can also calculate the variance. We can also calculate the standard deviation. Somebody asked for standard deviation, SD. You put in your reaction, and then it gives you your SD. So we created the first object, which we call reaction. We can create the second object, which we call reaction 2. Remember, if we don't differentiate, you replace the first objects. So let's create the second object, which you call reaction 2. This one has values of 50, 90, 150, and 500. Okay, so I have the object here. You can see it is also appearing in the environment. Reaction 2 is here. You tell it is numeric. It has 4 objects, that is 1 to 4, and the values are also in there. You can see the values from there. We can also calculate the mean of that object. We can calculate the variance of that object. So these are the same. If we create again our reaction 2, but we already have this reaction. So these are just a redundant. So we can create the same object again, get the variance divided by 8, and this is the variance of the mean. So the variance divided by the 8, that's the variance of the mean. And then we can create another object, reaction 3. We run the reaction 3. We can get its variance. We can get the variance of the mean. I showed you yesterday how why the variance of the mean should be less than the variance of a single observation. So that was these were the first few lines that you saw in my presentation. This is a simple line that already you did with Ellen. I just wanted to bring it out, and then we look at it again today. So the next thing that we are going to do is we are going to look at randomization in completely. We're going to use R to get for us a field or experimental layout for completely randomized design. So the first thing that we can see from here is written set.seed. So set.seed here allows us to get the same randomization if we repeat the process again. So if I want everybody to get the same randomization, we need to set the same seed. So this seed can be anything from 1,000, 2,020, whatever it is. So the first thing we have done here, we've set the seed. We can run that command. And then we are creating an object called F. And how is this object created? We first get a vector. So this vector has A as the first element, B as the second element, and then C as the third element. So we've got this vector here, and we replicate each value in the vector 4 times. So this command here will give us, we can actually run only this command here and we see what we have. So you can see here, A, B, 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 C, 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 okay? And then what do we do with that, what we have created? We convert it, we make it a factor now. We get another set of command on it, say factor that. So if we run this, we're going to have our variable, our object called F. We can also look at what is in F. So let me clean up here. I just type F in my console, and then I enter. And then, so it tells me F is this, and then it has levels A, B, and C. So it is a factor because we converted F into a factor. So we now have this A, B, 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 C, 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 C. So what we have here is that we have each observation, each treatment is replicated 4 times. So what we want to do then, we want to assign each of these 4 replicate to the different experimental unit that we have. So we're going to create this. This is a randomization process. So we use the word sample. So this is a function. So what does this function do? It from our object, which is A, B, 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 C, 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 it now tries to assign them to the 12 experimental unit that we have. So this command here, what it says that go to this set here, pick one element from that set here, assign it to our experimental unit number 1. Don't replace that one back. Go and now pick for experiment for set 2, pick for 3, pick for 4, pick for 5 until you finish all the 12. So this is what we call sampling without replacement. So we can create this. The good thing with R is whatever you created, you can actually see it straight away. So I can type here FSC and then I enter so I can see it here. So now you can see from here, B is coming first, C is following, A again, B, A, C, C, B, A, C, C, B, A. Okay, so in the first unit, it assigns B. In the second one, it assigns C, and so on and so forth. So what I want to do now is I want to create an object again. This object now is a simple vector from value 1 up to 12. So I can actually run this line and I can check what I've actually run by just highlighting this and running it. So you see now I've created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what am I trying to do in this case now? I want to have some kind of a field plan or an experimental plan. In the first column, I want to have my 1, 2, 3, 4, 5, 6 unit, experimental unit 1, 2, 3, 4 up to 12. And then in the second column, I will have to have my assignment, which we saw before. So we can, and then we want to make this a data frame. I think both Ellen and Susan talked about data frame. So we are putting all the information that we have now together. Please, when you're writing R, if you highlight this and you run, that means it will only run this part, it will not run the whole line. So what you need to avoid highlighting. Just put your cursor in anywhere in the line and then you run. So now we can see we have created an object called a data called plan, and this object should be a data frame. Okay, because that's what we have. We can print and see exactly what this object is all about. So you can see from here. Okay, now we say rat1 receive B, rat2 receive C, rat3 receive. So if you already have your rats, you level them already 1, 2, 3, 4 after that, then you can now assign your treatment simply. Okay. The other way that you can do is you can use the function design.crd from the package Agricole. The one we've done here is just doing it from scratch. This one here, we use now what is in the package Agricole. So if you've not installed Agricole and you've not loaded Agricole, if you run this one here, you're going to see red. So what do we have inside here? So the first thing that we need to do is we need to have our sets of treatment. Okay, our sets of treatment, we need to see whether that is, remember we have our F here. Okay, so F is our sets of treatment. You need to tell us, we need R, which is the number of replication. And then we need Okay, we talk about a series. I'm going to explain what a series is. Then we set a seed. Setting a seed means I can repeat all of us. If we set our seed to 50, all of us will get the same randomization. And then kind mean what kind of randomization we're going to have. Somebody has something called super duper. I mean, you can read more about it and then have. Now I'm going to run this. If it's going to give me an error, I have no problem. Whatever I'm going to do, I'll run and check exactly what my problem is. Okay? So it tells you error is not found. Okay, why is error not found? We need to specify the number of replication that you have. So let me first create a new F, the F that I have as, so I have A, B, C. Okay, so I'm creating an object here, a F. So in this case now, what I'm going to say, maybe R equals to 4. So this value is defined, this is here, and now R, we set it to 4, and then we are going to run again and see what will happen. Okay, this time we don't have an error. So it seems to be okay. Now we have created an object here called CRD design. This CRD design has several components. What this step does is we are saying, oh, let's get a component that we call book from the CRD object that we've created. What we could do, let me first clean up a little bit. We could actually use the function str, which is the structure, and we see what do we really have in this CRD design. We can run this, and then it will tell us what we have. So here, it tells you you have the design, you have treatment, you have replicate, you have series, which is 2, seed is 50, kind is super duper, logic. Then you see we have something called a book. And they tell you a book is a data frame. It has 12 observations of 3 variables, okay? And under that, you have a plot, you have a replicate, you have F. So we can extract one part of that, which is the book. So let's run the book, and then we see what the books gives us. Okay, so you can see here, it will tell us 101 rep 1 for A, okay? Rep 1 for C, rep 1 for B, okay? So what it's saying is that plot 1, plot 2, plot 3, in our case, we say rat number 1, rat number 2, rat number 3, rat number 4, rat number 5, rat number 6. So rat number 1, which is first replicate, will have A, rat number 2, rat number 3, rat number 4, and so on and so forth. Now I want us to go back here and change the series here to 1. Remember, we ran the series to 2 and we saw. So we are going to see what will happen when we change the series to 1. We can run that. So can somebody tell us what changes we have observed here in the chart? What changes have you observed between the book that we had when series is equal to 1 compared to when series is equal to 2? Okay, somebody said 1. Okay, so number plot change. Okay, so the plot change. Okay, so we can see what is happening. So let's change again to 3, series to 3, and run. Okay. Okay, so what's happening here? We first get 3 values, that is, we start from 100, and then the one now that levels the plot is in the 1,000 position. When we had it as 2, it will be in the 100 position. Okay. And then if you have it at 1, it will be the 10th or the 1th position as you have. So that's just the leveling. It has nothing really. It doesn't change much of what is going on. So we can have that. Okay, good. So what we have here is then you can level this as your rat. So maybe we start at 0 and we see what will happen. Okay. Okay. So at 0, we start complete at 1, 2, 3, 4, 5, 6. We start at the 1st position. At 0, we start at the 1st position. At 2, we start at 10th position. At 3, we start at the 100th position. At 4, we start at maybe the 1,000 positions, and so on and so forth. So that is the changes, but it doesn't really matter. That is just conventional naming of the plot. So we are done with the CRD. So you know how to now you can use ARA to design for your study if you're doing CRD. With this, then what you can do, you can as well put this already in your Excel, create this in Excel, and you also, what you need, you simply need now, you need to add the rows for the data collection, maybe plant height, maybe number of animals, and so on. You just need to create more column, then you have your data entry form also ready for your study. Okay. So the next design was the randomized complete block design. And we say with the randomized complete block design, our experimental units are grouped into blocks. Within block, there's uniformity, and then between blocks, there's the heterogeneity or their differences. So here, the randomization process is done block by block. So here, what we can do, we can randomize for the first block. So you already seen this sample. What are we sampling from this set here of our treatment, and how many times are you sampling? You are assigning it to 6 different units within our block. So the first thing that we need to do is we run that. And then, so we first one, we sample for block 1, we sample block 2, we sample block 3, block 4, block 5, and block 6. Okay. And now, so each of them, you can see what is in each of them. If I click on this, it will tell me in block 6, we start with D, A, E, B, C, and F. So what we can now do, we can combine them together. We create our set of treatment, we combine them together. Now, when you say C bind, yeah, C, you're going to bind them as vectors. So we can run this. And then we can also observe exactly what we have run. So we can highlight this and run it. So these are our treatments that you have. And then we also need attached to it the block. So here you can have, I want to get my, so the first thing that we are doing here is, this off. So we get our 6 blocks. We replicate 6 times each, so that we create a line of 36 that the line of not 36, 18 that we are going to attach to this one. So we create what we call a block, and then we can create a plot, and then we combine them together. Once we put we put them in different columns. So let's look at what we've got so far. Okay, so you can see here block 1, plot number 1. treatment A, block 2, plot treatment plot number 2, plot number 3, plot number 4. I think something is not right here. I need to check my okay, I think should be 1 to 6. Let's run it again. So remember, each block has 6 units, 6 experimental units. Okay, so here what we are doing here is we are getting block 1, plot number 1. And then you have block 2, plot number 2. This is also not correct. So when you can see now, you need to before you can run and start anything, you need to first try to look at what you produce. So every time you design, you come up with a plan, you need to check whether everything is going on well. So we need to go back and see. Okay, so I'm going to continue altering, and then I will see what will happen. Okay. So the next thing I'm going to do is, let me change this. I've not got it. Okay, so who has the solution to this? Can I see somebody who has the solution to this? In the chat, but I don't know, but you cleared it. Okay. Question: in this line treatment, that why stop in B3 not B6? Okay. Okay. So I think that could be, then the solution is there. So we have 3, 4, we have 5, and then we have 6. Okay, so let's see whether this is going to change for us. So I'm going to remove the repeat. Okay, it does not solve our problem. So what we need to do first of all is this. We have no problem with this. What we have here is we have our ABCD. So once we created this treatment here, let's look at it. We have this is perfectly okay. So the next thing that we need is we need our block to run from 1. We need block 1, 1, 1, 1 first, 6 of them. Block 2, 2, 2, 2, 6 of them. That is what we need now. Okay, so I'm going to do it the dirty way. So what I want to do now is I want to create these 6 of them. Okay, 1, 1, 1, 1. I go and create another one. This time is block number 2. I created 2, 2, 2. Of course, the command below this is a lot simpler. You just need to run the agricole command and you'll be done. But I don't want to give up. So we have 3, 3, 3. Then we have 4, 4, 4. Okay, then we go have 5, 5, 5. And then we can have 6, 6, 6. Okay, then I need to remove this. So if I run this, okay, so the next thing I need to do is to put my seed there, and then I close. I should be ready to go. Because I still have one bracket remaining on the side. That's why I have a rate. Let me just put my my one remaining bracket and we should be ready to go. One thing I'm sure is that the solution is there. Okay, so these are my blocks. I have 1, 1, 1 up to 6. So the next thing that I need to do is I need to, let me run this. And then let me try to combine and try to run my plan. Okay, so this is what I was trying to do. So you see plot 1, block 1, plot 1 has an A, and then a B, a C, and a D, and so on and so forth. I just hope, now it has A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. But that's fine. At least the thing here is that we have that. So for now, just not to waste time, let's run this other one from down here. And then I will be able to give you. So this is the easier one. You go and use the agriculture one, and then you have the design.rcbd, and after you run this, you print the RCBD, and then you have your 1, 2, 3, 4, 5, 6, and so on. So that is what we have in this particular case. I'm sorry for the mishap in that. I think I was playing with my command before I came here, and somehow I dotted here, but I still have a lots of red here, so I need to sort out my different brackets and commas. Something is not right in this one here, but I'll get back to that and we'll have that. So that is for RCBD. You can print this, put it into Excel, and then you add the different columns, columns for the names of the variable that you're going to measure. And then by then you have your field plan ready. You also have your data collection tool ready. So at the end of the day, you will actually have that. The next thing is to generate for Latin square design. So here we need to first create a set of treatments that we are going to, replicate to design that you are going to randomize. So here we have nutrition 1, 2, 3, 4 after nutrition 5. So we can run this. Don't mind about my red. My red here is because I'm lacking one of my lines have a bracket or an extra bracket or add a less or more, or there must be a comma somewhere, but it's not going to stop running out the other command. So here is still using the agriculture command, but a particular function design.lsd. So here we have the nutrition, which we have created here. And then here we have the seed. And we say the seed is important if we are to generate the same design. So we can go ahead and run that. We go for LSD. So here we can look at what we have designed already. So here you can see we have row and column, and then we have the different nutrition. So here So you can see 1, 3, and then, but what we need now, we need to level it up so that we have week and we have animals. So we go to our LSD. We look at the row, and then we are leveling the rows as instead of having row 1, we have week 1, week 2, week 3, and so on and so forth. And then we also do for the same for the column. And then later we see what the results. So 8, as you are told, it gives us the first 6 rows. So you can see here week 1, animal 1 received nutrition 1. Week 1, animal 2 received nutrition 4, and so on and so forth. So that will be for the Latin square. And finally, for the split plot. So the first thing is, remember in split plot, we have 2 factors. So we create treatment 1, and then we create our treatment number 2. So treatment 1 as 2, or treatment 1 or factor 1 as 2 levels. We have spray versus no spray. And then we have varieties, which is variety 1, variety 2, up to variety 5 or 6. So it's still the same agricole. So design here, and then the dot split mean we are designing a split plot design. Remember the other one, design.lsd for the Latin square, design.rcbd for block, randomized complete block design, and then design.crd for completely randomized design. So it's still the same thing that, so in this case, the main plot factor comes first, treatment 1, and then the second one is the subplot factor, and then how many replicates you want. And then if here, the thing here is that you need to decide which design you have. Remember, split plot can be with any of the design that we have. So here we say with the RCBD, and then we have the series. We know what the series does. And then we have the seed, the kind, we have randomization, and then we have that. So we can run this. The objects are not found. So we first need to be able to define the treatment 1 and treatment 2. So once we have them there, we can then run, and then we have that. So the thing with R is you don't need to see red and then you start having self-pity and start saying, oh, I'm done today or what. The thing is you need to find a solution. You see how I was struggling with just a simple solution that probably somebody's already done it there. But at the point of running it, it may actually be different things. Okay, so we can see now split plot, block, and then the treatment. So here you would see the 1, 1, 1, 1, 1, and then the splitting. So the first, this is our main plot 1. And then the main plot 1 is splitted into subplot 1, 2, 3, 4, 5, 6. And these are all in block 1. And then we have here the spray as the main plot factor. And then the different varieties are split to have them. So variety 1 on 1, variety 3 on 2, variety 5, variety 6, and so on and so forth. Then you go to the main plot number 2. And then you also see what has happened. You go to number 3, you go to number 4, and so on and so forth. And then finally, we can also generate for balancing complete block design. So here we have what we call balance BIB. Of course, the first thing you need to do is you need to create your object for the treatment that you define. So I can have that, and then I can run BIB. I can extract what is in the book. Okay, so here it gives you even the different parameter. This is the parameter of BIB. Lambda equals 2, treatment means 4, block size 3, blocks 4, and replication 3. So, and then it tells you where to assign which treatment in which block. And then finally, we can create our lattice. So my second finally, we can create a Latin, the alpha lattice design. So here you need to define the treatment. Remember, in this case, the treatments are very many. So here we have 100 treatment. So we can get T. T is supposed to be the length of the treatment. In this case, this is what we have. The length of this, which is 100. And K, remember K we say is the number of unit within the block. And then S is equal to, S is the number of unit that the number of blocks that you need to group together in order to create a complete replicate. And here we have 2 replication. So once we define all these factors, we can then run and check our book. So let's see what is in the book here. Okay, so we can see the different, these are the plots, these are the different units. This thing can be annoying. Okay, so I have my plots here. I have columns, I have blocks, I have treatment, and then I have replication. So column, so here we have block 1, treatment 47 in replicate 1. So we can have all these. So here they have them in columns. And then we can go ahead, create the plots, the dimension like that, and then we can have the sketch. So this is the sketch that you can actually have within, you can use it for your analysis. So here, rep 1, these are the different treatment within rep 1, and then you can have the treatment within rep 2, and so on and so forth. So these are this thing should have not taken us this long if it were not because of this stubborn line that I'm going to correct. So for now, unless there's some question, I will then have to hand you over. Okay, somebody's trying to solve the problem, which is okay. Yeah, so I think that's fine. Okay, so I think now let me hand you over to my colleague, Ellen. I'll still correct my lines, but I also think it will be a challenge to each one of you to run the lines and see. Let me just correct my line, then I share it with you. So thank you for now. I think I hand you over to Ellen. No.
I continue? Yes. Okay. Good morning. Can you hear me? Okay. Thank you so much, Dr. Thomas. Now we are going to move on to overview of sample surveys. Okay, let's start. I understand it has been a good moment when you're looking at experimental designs. Now let's see, what about in case you want to determine a sample size if you're working with surveys. So this time around, we are still continuing today. Hopefully time will allow, and then we get into R and see how you can determine a sample size that is sufficient for your study, such that by the end of the day, it enables you to get the desired results that can support you in achieving your objectives. Okay, so we are looking at overview of sampling surveys. And we are going to look at a simple introduction of sampling methods, and then we see how do we move on. But it's important to first understand what a sample survey is. So most of the time, we want to collect data, okay? And looking at the population, it is very big. Our whole population is very big. But we want to get a sample that gives us a proper representation of the whole population. So in that case, we go to what we call a sample. We get a sample that is drawn from the population survey. So the point is that we want to draw inference about the population by using a subset of this particular population, which I'm referring to as a sample. So we can draw various conclusions or inferences. For example, in case you want to look at people's opinions, study their behavior, attitude, the different levels of income, name it according to how your research process is. I still understand that yesterday there was a detailed discussion on how you can, on the different processes, on how a research process looks like and what is entailed. Okay, so now as we push on, like I mentioned earlier, most of the time, a good survey aims to select samples in such a way that they can collectively represent the underlying population. So the point is, in case you pick a sample, can it really give you similar characteristics that you expect from the population? In other words, you want to see whether there is no bias in the selection that you've done. And this is usually done through a random process. So, but nevertheless, we also have to note at the back of our mind is that there are some errors that are involved in case you're dealing with sample surveys. Because remember, because all the elements that are picked from the population, or not all elements from the population are selected. So there is a possibility whereby you might pick a sample and you fail to estimate the true estimate or the true estimated value of the population. So in that particular case, like I said, we cannot avoid error, so we call that a sampling error. It's not avoided. Thomas has just discussed yesterday about experimental designs. And also we saw that still in experimental designs, there are errors, okay? And still as we're going to move on to regression, we are going to see that there's also an error. But then the point is, how do we see that we try to see that this error is as minimal as possible? So because all elements of the population are not selected, it is possible that the sample best estimate value may not exactly match the population value or the true value. So then the difference between the estimated and the true value, the true population value, we refer to that as a sampling error, or you can call it the margin of error. All those words mean the same thing. Okay, so sometimes you can ask yourself, why shouldn't we go in for the whole population? And then we simply say that, well, a sample, let's go in for a sample surveys other than considering the whole population. Of course, we have to put in mind that certain issues or resource, for example, resources, including time and then funding. Maybe, for example, in case you're going in for data collection, and by the time you write your thesis, you only have, for example, we can say 2 months or 3 months. The time can be a constraint. And so instead of taking the whole population, you decide to go into what we call a sample survey. So surveys are sampling designs that are selected in a way that you would want to minimize sampling errors. Okay, so, but it's very important to note that we have to ensure that the sampling error that we get, it has to be as low as possible. In most of the literature that you will see, most of the time the marginal error or the level, the acceptable error, it's plus or minus 5%, that is 0.05. Well, it depends on the study and the objective somebody wants to achieve. For example, in case you go into the medical field, it could be like the 5% is very big, and you have to say, maybe they reduce it to 3% or 1%, because in that particular case, remember, you're dealing with human life. So you have to ensure that your level of error or the sampling error is as low as possible. So let's take this particular example. For example, it says that an opinion poll on Uganda's health concern was conducted by the GAP organization between October 3rd and 2020. And the survey reported that 29% of adults consider AIDS is the most urgent healthy problem, with a margin of error of plus or minus 3%. Then the result was based on telephone interview of 872 adults. When you look at this particular statement, there is a lot of information that has been condensed in these 6 lines. What we can look at, when you look at the study population, they considered adults. And the estimate they are giving us, they're telling us that is 29%. So that is the point estimate, or the estimated value, 29%. And the margin of error, we are having this particular case. Remember, here we are dealing with the human population. It is plus or minus 3%. How was the data collected? We are told that there were phone interviews, and then the sample size was 872. So most of the time, for example, as you're reading different newspapers, you can come across such information. And then in case you've got prior information about surveys and how they are being carried out, so it is always easy for you to come up with meaningful information. So basing on that particular example, there are 2 responses, okay? The yes and then the no category, because the question was that is it that AIDS is an urgent healthy problem? So the estimate we got, it said that 29% from here, 29% said yes. So since it's a binary, then the other fraction, the response would be no. If you had about the Bernoulli distribution, so we've got the probability, which will be the probability of success. In that case will be 0.29, and then the failure is 0.71. We can still get the total number of respondents that said yes, and then those that said no, by multiplying them with the sample size that was given to us as 872. So as you're reporting, or as you're going to do your survey, it is always important that you get to know what is your sample size, or what is N, what N are you going to use, such that by the end of the day, it is able to support you to achieve your objectives or the conclusion that you want. And in case somebody replicates that study using the same size N, that person can also come up with a similar result. So, however, sometimes it's also important to understand, yes, they say 29%, okay? They say 29% say it is really a healthy problem concerned. But as a statisticians, or we need to ask ourselves, they say 29%, but we need to ask ourselves, how much confident are we? So from the basic statistics, we've been looking at most of the time, the confidence interval is constructed around 95% confidence interval, but still it goes back on what exactly you as an individual want. Do you want to check at 95% confidence interval, at 99%, or at 90%? So we know that when you check in most statistical books, we are going to find this particular formula whereby we are getting the estimate, that is our P, the estimate we are having. So in our case, which is 29%, that was what was given to us, that people said, yes, it was a healthy concern. We need to, our degree of confidence, this is the Z value, 0.095, which we are taking at 95%. And then also the standard error of the estimate, because remember what we talked about, that still, however much you're doing these surveys, there are errors that are being involved. And still, how do we calculate the standard error of the estimate? This is the formula here, PQ over N and the square root. It comes from the variance. and we need to still minimize the variancy as we can. I mean, basing on the estimate that we have, okay, basing on, we know that P, that is our estimate that we got, that it was 29%. And I say the other fraction, it is the Q, or the ones that responded that it wasn't a healthy concern. And when you calculate this, when you move on with the calculations, I'm going to go into a lot of details. You can see, we are saying that we are 95% confident that our estimate lies between plus 0.02 then to 0.32, this 29%. So in other words, from the question or from this particular statement, we've been able to derive out the confidence that is being used, and also we've been able to use the N. We have the N, we have the P, we have the Q. It's a matter of substituting in everything. But I want you to see, basing at 95% confidence interval, what range can we take to say that, well, our estimate was 29, and the level of confidence basing on the 95%, it lies between 0.26, that is 26%, and then to 32%. So, I mean, but when you come back here, whatever they are doing in this basic example, what we are having here, the P is our estimate, plus or minus, that is, we can consider the whole of this expression on the right-hand side as our margin of error. And we are able to calculate what the margin of error is. So remember what we had in the statement, it was plus or minus 3. And we saw that we still proved that in this particular case, it is 0.03. This is just a summary that we get the estimate, then plus or minus the margin of error. Because by the end of the day, we want to ensure that the true estimate, which is obtained from the population, and the true estimate is what we have that is estimated from the population. However, when we're looking at the sample population, when you're looking at the sample, sometimes we are not so certain that the estimated value is going to be equal to the estimated value is going to be equal to the true value. So that's why we put that part of the sampling error and we put a plus or minus. So what I have here, it is the same thing. Like I mentioned earlier, the margin of error was equal to the whole of the right-hand side. So the point was just making here we did, everything was brought back, whatever the values are, and then made in the subject. So the point is that the moment you know the estimated value, then it will be easy for you to be able to compute the sample size, of course, with a specified margin of error that you are interested in. Because by the end of the day, if you have your estimated value, you can be able to tell the other fraction. And then also, basing on the confidence, I mean, these are statistical inputs that are already there that you want, whether it's 95 or 90% confidence interval. And then you can be able to compute the sample size. So by the end of the day, because what will this help you? It will help you to either determine whether you need a large sample size or you need a small sample size. Okay, let me check in the chat. Are we on the same page up to there? And somebody is asking about today's material. Please check the Google link. Everything is there. We put materials up to day 5. Just paste it in the Google and then download all the materials that you need. Okay, now let's move on to the types of survey designs. Of course, there are many, and they also depends on the kind of study that you're looking at. But the commonly used one, we've got the cross-sectional surveys, whereby in this particular case, data is collected at a point of time, okay? We've got longitudinal surveys. When you look at, of course, longitudinal surveys have got different ways of how data is being collected, but the data is collected repeatedly. When in case you're considering trends, in this particular case, these ones usually the surveys take a very long time, and the same sample population is being looked at over time. And then in case you're considering a cohort, then it implies that you are studying the same cohort over time. For example, you can take maybe postgraduate students that have entered maybe in this particular academic year, and then you keep tracking their progress until when they graduate. That is a cohort study. You're tracking the same population or the same group of people. And then with the panel, we are studying the sample of respondents at various time points. So in this particular case, you are looking at the respondents themselves. Maybe you're looking at people, you're tracking out people with maybe with cancer, and you're trying to check whether there is a progress in medicine. It is just the same person. What if you give them treatment? What happens after some time? It is the same person, and you're trying to give treatment. Would you be able to track different variations and check whether the drug is doing well or not, among others? Okay, and then we can also look at the different sampling procedures. Under here, we've got what we call non-probability sampling and then probability sampling. So it still goes back. What exactly do you want to look at? Under non-probability sampling, we have conveniency, we have judgment or purposive sampling, we have proportional sampling, and then snowball sampling. So here, like the way you have the word non-probability sampling. So whatever decision that you take, it is not going to have any probabilistic form in it. So, but it will depend on what, maybe there are some populations, as we are going to go to discuss in details, that sometimes tricky to get, or they are unique in their own way. And maybe you might need to use a snowball or conveniency, but we can discuss that as we move on. And then probability sampling, we are going to look at the various types. We have simple random sampling. These are probabilistic in nature. We have systematic, stratified, and then cluster. But when you look at all these types of sampling procedure under probability sampling, they form what we call multi-stage sampling. So you can start from you can have a stratified, then you move on to cluster, and then later when the different methods of probability sampling are being used, we do call that a multi-stage sampling. Most of the time, especially when you're looking at national surveys, because remember, it is looking at the whole country. So you can apply the multi-stage sampling. But let's go in details and see what each means. But before you move on to do the sampling, the survey sampling, it's always good to understand what are the different characteristics of a good survey. Number one, it has to meet the requirements of your study objectives. Remember, the objectives that you set vary from study to study. So by the end of the day, you need to think twice and say, in case I choose this particular approach, will I be able to meet my study requirements, among others? You have to look at also the time consideration, which I mentioned about already. You are a student and you expect to graduate in 2 years or 3 years. But then, in case you're going to use a survey to collect data collection. Is it does the time you have reasonable and timely, such that you're able to complete on time? The issues of cost consideration are also important. And also, when you get to the sampling issues, you need to ensure that the sampling procedure that you use produces the best estimate, whereby at least it approximates to the true value. And then also, the sample size should not be too low, and then should also not be too large. I've already mentioned we need to ensure that we have an unbiased estimate by keeping the error as minimum as possible, among others. Now let's move on to details about the different sampling methods that I discussed about. And we're going to start with the simple random sampling. Understand that at least most of us have come across this particular term. With the simple random sampling, yes, it was also talked about it yesterday when they were covering experimental design. whereby in this particular case, this is the simplest among all the choices. There is randomization, but also what is important to note that every element has an equal probability of being selected from a list of all population units. So you assume that when you go to the field or when you go to the survey, the respondents that you're going to pick, everyone has an equal chance of being selected. In case you have a list of all your population units, maybe, let me say, for example, if you're going to use students, so every student has an equal chance. That is simple random sampling. And remember, n is gotten from the capital N. Small n, that is our sample size, and then capital N is the population size. So we need n that will be able to give us a similar representation if we had used the population. What about systematic sampling? So when you look here, according to Levy 1999, when it comes to systematic sampling, either by itself or it could be a combination with some other methods, maybe the mostly wide used method of sampling. Like we said, there are various methods, but also when you're going to pick your own sample that you need, it depends on whatever sampling approach you're going to pick will enable you to come up with the required sample size depending on the objective of your study. So when you check from Kish in 1965, still he still further confirms that a systematic sampling is also a more widely used method. Well, it still goes back, and it's also another alternative for random sampling. But what happens under systematic sampling? The way you hear the word systematic, though something unique with this particular approach is we randomly select the starting person or the first unit. If you're dealing with objects or with human beings or any respondent, depending, then you are going to select the first unit or the first respondent, and then the rest of the other respondents that you're going to include in the sample, they will be obtained depending on a predetermined pattern. And there is a concept what we call a systematic sampling interval. And how do we get a systematic sampling interval? Most of the time, you know what your n is, okay? That is the population size, but you want to get n, and you know the sample size you want to pick from the population size. So for you to come up with a systematic sampling procedure, this will be equal to the population size over the sample size that you want. And then the systematic sampling interval that you get, it will be the one to give you the pattern that you're going to take, okay? In other words, if you want to select n units from your sample and you've already determined what your first unit will be, the first R. So the moment you determine your K, which I'm calling the systematic sampling interval, then so after picking the first unit, then you pick the kth part. Every kth person that will be picked will be contained or will be added in the sample that you're going to use. Okay, so let's take an example. In this particular case, in case you let the population size to be n and it's 100, and then you want your sample size to be 10. So it implies that your systematic sampling the systematic sampling interval, it's going to be 100 over n, and you're going to come up with, you'll come up with 10. So it implies that you will pick every 10th person. As you are having your list, you pick every 10th person and will be part of the sample that you're going to get. So what you're going to pick, the first person you're going to pick will lie between 1 and then the 10, okay? The kth term, which I'm having here, that the first person that you're going to pick, it has to lie between 1 and then the predetermined interval, our K, the systematic sampling interval. So assuming that in this case, in case you pick 7, then it implies that, remember, we are picking every 10th person. So we are going to start from 7, and then we count up to when we get to the 10th person, and then that person will be included in what? In our sample. We skip the rest, we go ahead further on the 10th person, and then that person is included in the sample. And so on, etc. So now let's take this particular example. Assuming that I've got this particular list, I'm having 100 respondents, and what I want my sample size to be 20. Okay, so for me to get the K, which is equal to the population size divided by the N, I'm getting 5. Okay, so we need to select our first number that lies between 1 and 5. So in case I pick 4 here as my random person to start with, then it implies that I'm going to count from 4. Within my list, I'm going to count. And so the moment I get to the 5th person, I'll include that one in my unit to compose, to be part of what? The sample size I'm going to pick. For example, in case I start with 4, then I'm going to count 1, 2, 3, 4. Then the 5th person is the 9th one. So this person is going to be part of what? My sample. I do the same till when I get the 5th one. Then I pick that particular individual. I include the respondent in my circle, and so on until when. So when you're looking at this particular frame that we're having here, so it implies that of the 100, whoever was in these positions of 4, 9, 14, 20, 19, 20, 24 was included in the what? In the sample size to make my N to be equal to 20. So these are the people that I would include. That is basically the systematic sampling procedure. What about stratified sampling? Okay, under stratified sampling, in this particular case, we are looking at the population is partitioned into groups. If you know the word to partition, it's like you're grouping into different groups, and we call these ones the strata. And the sampling procedure is performed separately within each stratum, implying that assuming, as we are going to move on further, for example, in case you've gotten a group of, let's consider gender, and you're looking at male and then female. So within gender, I partition into 2 groups. I get one group of males, and then I get another groups of what? Of females. Then what happens in case I go further into the sampling, then it implies that now the female group is going to form a stratum, and then the male group is going to form a stratum. And it's within these stratums that I'm going to go further and select the people I want to include in what? In my sample size. Okay, still more illustration on the stratified. I'm saying that the stratum variables are mutually exclusive. In other words, they're overlapping or they are disjoint. There's nothing that is common between these two. Okay, they have no intersection. Let me say like that. For example, we've talked about you can take the areas, urban and then rural. You can look at the economic categories or the geographical regions, the race, and then the sex. But end of the day, the point of a mutual exclusive, you have to keep it at the back of your mind. It's important. And then after, you're going to select elements from these different stratas. But it's also important to note that the population or the elements should be homogeneous. Okay. For example, in case you're talking about if you're picking sex and then you stratify into males and females. So we are saying that you have to be homogeneous within the stratum. So you have the stratum for the females, and then you have the stratum for the what? For the males. So they have to be homogeneous within. You're only having the females, and then you're only having the males. But they should be heterogeneous between the what? The stratas. So what is the main principle of stratification is to reduce the sampling errors. Can we ensure that we make the sampling error as low as possible? I've already mentioned that the most important thing when it comes to the basic rules when you're trying to do stratified sampling, always within, at least you should have a minimum of 2 elements being chosen from each stratum. Okay, so in this particular case, you'll be able to estimate the sampling error from all the strata independently. I've talked about homogeneity within a stratum and also heterogeneity between the strata. That is stratified. Now let's move on to the other one, which is called cluster sampling. We need to distinguish between, we need to understand what these sampling procedures mean, such that by the end of the day, we are in a position to use them in our research. Because by the end of the day, in case maybe you're writing a publication, they'll ask you, what procedure did you use to determine the sample size? How did you, maybe in case your N is equal to 20, or in case your N is equal to 800, there'll be questions like, how did you come up with the 80? Maybe it's because, I mean, different studies have different sample sizes. Okay, now, what about cluster sampling? So in this particular case, when we talk about a cluster, it is just a group of population elements, okay? Within this group of population elements, they are the ones that constitute the sampling unit instead of a single element of the population. Please note, we are using a group of population elements and we are not considering a single element of the population, because sometimes maybe some people find it hard to distinguish between a stratified sampling and then cluster. So in here, we are using groups of population elements, and the groups that we pick are the ones that constitute our sampling units. We are not considering single elements within the population. So most of the time, when it comes to cluster sampling, the clusters are the first sampling units, okay? We are going to, let's move on and see. Assuming that in this particular case, I've got a cluster population. I've got population 1, 2, then 3, 4, and they have up to 12. So within this cluster population, there are groups, okay? They're being grouped 1, 2, 3, 4, then 5, 6, 7, 8, then you have 9, 10, and then 11, 12. So now, so what happens here, I pick 2 from these clusters that I'm having. I further go ahead and I pick this one, the 5 and 6, and then I'll pick the one of 11 and 12. So whatever that I pick, these 2 that I've picked out of the 6, they are going to be, these are the ones that I'm going to include in my sample. The 2 clusters are going to act as my sample. It's what I'm going to base on. I have a big one, the cluster population. It has got 6 clusters. But then for me to get a sample, what I do, I can pick any of the clusters randomly. And in this particular case, with the example with the illustration that I'm showing you, I've picked only 2 clusters. So by the end of the day, we're going to see that in case there are 2 possibilities, in case you pick these 2 clusters, you can be able to use all the respondents within the same class, within these 2 clusters, all of them to be part of your sample size. Or you can say, you can go ahead and do a second selection, as we are going to discuss, which we call the secondary sampling units, but the first sampling units, and that is very important. I encourage you, in case there are questions, please post them in the chat, and then my colleagues will answer them, or I'll echo them out as I continue. So this is just an example when it comes to clusters, to cluster sampling. For example, in case you've got 10 schools that have got the same number of students across the country, if there are 10 schools, you can, each school is a cluster, okay? So you decide to pick out only 3, the 3 out of the 10. So these the 3 schools that you picked out of the 10, which are your clusters, they're going to act as your sample. When you look at this particular diagram here, they're saying that you pick whatever it's within a cluster and go ahead and use it. You can also still randomly select. And then the other thing that is also important about selecting sampling selection procedures, like I mentioned, when you come to the clusters, the moment, for example, we talked about the 10 schools and you pick out 3, we refer to that as the primary sampling unit. So the 3 schools will act as our primary sampling unit, implying that you select them randomly, and then you're going to include all the respondents that are in there into your sample size. However, you can go ahead and do another selection, either by using a simple random sampling, or by doing a simple random sampling, or a systematic sampling, depending on what you want. And if you do that again, then we refer to that as the secondary sampling units. Okay, and in this particular case, maybe now you specifically want to get onto the respondents themselves. So in case you select all the elements or the objects that you've selected within, you can select all the elements. That is just for your convenience to include in your sample, or you can still further do simple random sampling and just get a few from these clusters that you've picked. Okay, so there is what we call the simple one-stage cluster sampling. In this one, like I said, you list all your clusters. Like in the other example we had, where we had 6 clusters and we chose only 2 clusters to act as our sample. So you list them all and then you select from the list. So in case you select the clusters, this is usually, you do it by simple random sampling strategy. So under simple one-stage cluster sampling, it implies that you select all the elements within the selected cluster to act as to be part of your sample size. You select all the elements and then you include them in your survey. However, that is the simple one-stage cluster sampling. We also what we call the simple two-stage cluster sampling. It still starts with the first one. You list all your clusters in the population. Then after that, you select the clusters. Remember, we talked about the 10 schools, okay? Then you select 2 to act as your cluster within the sample. How do you select them? We use a simple random sampling. But in case you go further, within these 2 clusters, or the 3 clusters that you've selected, and further do simple random sampling to specific elements or object, or you can use systematic sampling, then that second stage we refer to it as simple 2-stage cluster sampling. And we can have all these clusters, like I mentioned earlier, multi-stage sampling. Multi-stage sampling, this one involves more than one type of sampling. For example, like I mentioned, when you're looking at national level surveys, most of the time they perform a multi-stage sampling, whereby you involve stratified. After stratifying, you group them into clusters. Then after the clusters, you can go ahead and either do simple random sampling, or you can do a systematic sampling. And whatever that you end up with will be part of your sample. So that is the multi-stage sampling. Here's just a simple example. Remember, it's multi-stage, so there are various stages that are being involved. Sometimes when you read in various textbooks, it is the hierarchical sampling. So maybe you can start with the regions. For example, within Uganda, we've got different regions, the north, east, western, and so on. Then from the regions, it's like you're subsetting. You start with the big thing, then you keep then you come, in this case, if the region, you come to the districts, and after the district, because the districts are within the regions, then after the districts, you go further down, you move on to the villages. And then the moment you get the villages, you can further move on to households, and then select the elements that you want. So most often it involves the multi-stage sampling involves several sampling methods, like I mentioned, the stratified, the cluster, and then simple random sampling. All right, this is just an example that you can talk about. Let me check in the chat. Are we still on the same page? PP sampling, we are going to look at that. All right. Okay. Great. Now, somebody was asking about the PP. I think we are heading there. So the big question is how to select clusters or the primary sampling units. There are two common procedures. First, we talked about simple random sampling. In this particular case, all the primary sampling units have got equal chances of being selected. In this case, we are saying that they have same selection probability. That is an equal probability method. However, there are also another scenario whereby you can pick, you can use the probability proportional to size approach in case you want to select your clusters. Why probability proportional to size? Because you want to get a clear representation of your sample. Probability proportional to size, it implies that the probability of selection depends on the size of your primary sampling units. In the sense that if you've got a cluster with a large size of your primary sampling units, then it implies that the probability of selection will be higher in that group compared to where the size is very small. So that is the PPS, probability proportional to size. In this particular case, there is an unequal probability method that is involved because we depend on the size, and then we go ahead and pick our sampling units. That is the PPS. Hopefully I've answered the one that was asking about it. Okay, so now with the probability proportional to size, as we continue, it's most of the time it's a preferred method of selection, especially when you're selecting clusters. Basically, of course, there are many reasons, but mostly large areas are more likely to be selected. And so it implies that the large areas means a large representation of the population. So, and when it comes to a large representation, then also basing on that, you'll be cost-wise, it will be less costly other than moving, picking few elements in a large population and then moving on to another one. And then also, the other thing is that the secondary selection units have the same selection probability. So it doesn't matter which one you're going to select info. So that was the part of the key points that you can really take under the sampling procedures, whereby you talk about the ones that are probabilistic in nature, where we have the simple random sampling, the systematic sampling, the stratified, and then the cluster sampling approach. Now let's move on to the non-probability sampling techniques. So like we mentioned in the previous slide that was there, we have what we call convenient sampling, from the word convenient, okay? So in this particular case, maybe let's assume that you're doing a study within a university, and one of the reasons that you can give, I'm going to consider maybe, I'm a student, I'm going to consider students as my case study because it is one, you could say it is convenient and I can easily interact with them to get the data that I want. So it is convenient, but it's also, it goes back on the type of study that you're looking at, such that by the end of the day, you ask yourself, I'm working on study A and B because of this and this. So the convenient sampling procedure will be the one that will be appropriate. And all these other ones, what we are looking at, they are all non-probabilistic in nature. So that is the convenient. So it helps a researcher to avoid problems of a sampling frame. So, but you have to ensure that most of the time the selection is often subjective. Another one is called judgmental or purposive. In this particular case, you said the groups that are being selected to be involved in your sample, you have there is a purpose. There is a certain characteristics of interest that you're really looking for. And I gave an example here. For example, maybe you're interested in people growing bananas in a particular village, and so as you're designing your questionnaire, or as you're going to move out to go ahead to do data collection, so you will specifically target that group because it is where your interest is. It is the particular group that you want to do research on, such that by the end of the day, you are able to come up with the informed decisions. So you target a particular group for a purpose. Here we say maybe they are good growers of matoke, or they are good growers of beans, and so on. So you purposely go into that particular group. Okay, then we've got what we also call snowball sampling. It is also a non-probability sampling technique, and it's most of this kind of approach or technique is mostly used in hidden populations. Sometimes maybe there is a study being carried out, and getting the people to include in the study or on the project is quite tricky. However, for example, some hidden population, let's talk about drug users, because yes, you know that within a particular country, it is illegal. But however much it is so, but there are people who still do what? Who are drug users or drug addicts. And so what you do, in case you know only one person, okay, who is a drug addict, so sometimes in case you're going for data collection, maybe you can use the key persons within the village, or you can use the chairpersons. They'll be able to tell you well, because they know that the people in the village very well. And there are some key persons that you can get, and then they can direct that in case you get so and so, you will be able to get other people. So you start with one person, it is snowballing. This person leads you to another one. Then each person that you get, you preach the gospel. Then the sample keeps on extending until when you get to the appropriate size that you want, and then you stop there. We can also, the other hidden group, you can talk about the prostitutes. If you get the leader, can also, or the lead, that is the leader of the association is able to lead you to other prostitutes. And then you can also ask them, and you can include all those particular people within your sample. And there's some ethics, and they're really important. That as you're going to some issues of sampling surveys, for example, you need a prior informed consent. You're not going to force things out your way. And you have to also be keen in case you're dealing with a sensitive topic. How do you clearly say it out such that no one is offended? And then the issue of confidentiality, talk about the legal requirements before going in for after designing the survey, before going in for data collection. And there are some legal requirements that needs to be done. Do you need to seek permission from the relevant authorities within the country, and so on. Of recent, different universities have got different review boards. Then later, that they can give you permission to go ahead and go ahead and collect your data. You can as well also look at the feedback of the data providers. All these issues are under the ethical consideration that you need to put into consideration. Okay, now let me check in the chat. Are we on the same page? Any question from what we've discussed so far? Okay, I'm only saying yes, 100%. I guess I've got a very good class today. Yes, Boris, please, if you have a question, post it in the Q&A. We'll have an answer, and then we can go ahead. I talked when I was explaining about the clusters, we looked at the cluster population, all right? And then from the cluster population, assuming there are 10 of them, and then you can pick 2 out of the 10 clusters to act as your sample. So after that, there are 2 possibilities. One, you can consider these 2 clusters to contain all the respondents. You can consider everyone within these clusters to be part of your sample. That is number 1. That is the 1-stage cluster sampling. Or you can move on to the 2-stage, implying that from the 2 clusters that you've selected, you can either use simple random sampling or systematic sampling, and then get the respondents that you want to put to be part of your sample. I think that was Boris's question. Okay. Is snowballing sampling used in sampling of household for an interview of certain areas? Well, Solomon, like I say, this one is with the snowballing, depending on the study you have, in case it's not a hidden population and you can easily get the respondents, then you might think of other approaches that can support you. But in case it is tricky for you to enroll people to be part of your sample size, then the snowball approach would be the right approach for you to go in. The point is, how do you penetrate within the community such that you are able to get this one person that will lead you to other people. For some of you have worked on projects, most of the time they recruit people that with whom they call, is it community, are they community officers or something of the sort? I'm not so sure. So they can support in getting people on board, the ones that are the one you want to call your study participants. All right. Okay. Okay. Beatrice is complaining about the speed. Fine. Let me reduce. The rest are saying it's okay. Now let's move on to sampling size and then the power of estimation. So what are the key things? Given that now we know what a sample survey is, what a population survey is, we now know the different approaches of the sampling procedure, the non-probability techniques, and then the probability techniques. Now let's move on. Having done all this, because these are procedures that you need to come up with small n, the sample size. So now let's go ahead and see, how do I determine my sample size? Remember, the sample size that I need to get, it should not be too low and it should not be too high. But by the end of the day, it has to be sufficient enough to support me to achieve the objectives of the study or the objectives that you've set for your project. Okay, now, maybe most of you have come across Cohen because it's one of persons that went ahead to talk about how to determine a sample size in his textbooks. Cohen, 1977. So he says that in a planning of a sample survey, a stage is always reached at which a decision must be made about the size of the sample. The decision is very important in the sense that too large a sample implies a waste of resources, and then too small a sample diminishes the utility of the result. So the point is here, what Cohen is trying to communicate is that we need to get a sufficient sample size that can support us to go ahead and get our objectives, not too large and then not too small. But how can we determine a sample size that will enable us to achieve the set objectives? So the question is, in case you are moving on to the sample size estimation, so you need to ask yourself, what is the appropriate sample size for my study? And then after having that question at the back of their mind about the size of the sample, and then you can also ask yourself that what is the size of the sample which I can use to generate the results on the population which I am going to study. Now, of course, there are many possible answers that you can think about. But what is most important, you need to think about what is the purpose of your study, because if you have no purpose, then what is the relevance of you getting the sample size? In other words, those are the objectives I've been talking about. You also need to think about the population size. There are some circumstances whereby, in case, for example, if you're using systematic sampling, you need to know your N, the capital N, the population size, okay? And then also the risk of selecting a bad sample, that can also affect when you're selecting your procedure. And then what is the allowable sampling error, or call it the acceptable error, or call it the allowable margin of error. Remember what we are saying, we need to see that we are trying to keep it as low as possible. So apart from the answers, the possible answers that I mentioned earlier, for example, about the purpose of the study, the population size, and also the allowable sampling error. This is also important to add the 3 criteria as you want to determine the appropriate sample size. And these are the level of precision, the level of confidence, that is the risk. Yes, I've been sharing what they are, but we can still push on and see what do each mean in more details. Because by the end of the day, when you look at these attributes, are the ones that are going to support you to make a reasonable sample size, and also the degree of variability in attributes being measured. Yesterday, when you're looking at experimental designs, I had a new concept, a lot of variations that you need to reduce the background noise, the variations such that you're able to reduce the error as you're doing sample experiments. I mean, so sometimes the information that you cover in experimental design, it is also similar to the one that we cover when working on surveys, but the point is understanding when to apply what. Okay, so now let's talk about the level of precision. It was explained yesterday, but maybe in a simpler way, I would say that it's also known as a sampling error or the margin of error. We've already mentioned that depending on the study, but most of the time, the level of precision, we take an allowable error of plus or minus 5%. And sometimes when you're working out this particular section in maybe you're writing out a paper or you're writing out a thesis or a dissertation, it is always good the moment maybe you're quoting your sampling error to be plus or 5% to also quote the literature to support that particular evidence, because there's a lot of literature to back up the 5%, and maybe some, like we said, depending on the study, especially with the sensitive studies, maybe it can be reduced to 3 or 2%, but on most textbooks, it is a plus or minus 5%. It's also good to back it up that according to maybe so and so, putting the author and then the year, the level of precision I'm considering is 5%, because it's quite interesting that some people can go ahead and say, well, I'm going to consider it as 5.5%. And then when you ask this person why, and they have no reason, he just tells you, I think it is okay because I've seen it. But it's always good to back up your information. That is the level of precision, or the allowable error, or you can call it the sampling error. Let's take an example. We have an example here that says, if a researcher finds that 70% of the students in the sample have adopted a recommended practice of submitting the assignment, we are given the precision rate of plus or minus 5%. We have a plus or minus. Remember, we are not so certain of the true estimate. So what we do, we want to estimate the estimated value to have a certain allowance, because we are not so sure that we'll be able to estimate the exact population value. So what does this imply? We are having 7%. So it implies that we can conclude that between 65 and 75% of the students in the population adopted the practice. Remember our estimate, what we had in the first slides, plus or minus 5. Okay, that is the allowable error, or we can call it the precision rate. So we will be confident to say, well, between 65% and then 75% of the students in the population have adopted the practice. The other one's about the confidence interval, which I've already mentioned about, and sometimes it is referred to as the risk level. Still, like I said, well, depending on the confidence that you want, but most of the time we use a 95% confidence interval. You can push on to 99% or 90%, depending on what exactly that you want to work on and the nature of your study. So when we are looking at on the confidence with the confidence interval, most of the time this theory is based on it's based on the central limit theory, whereby when the population is repeatedly sampled, okay, you sample the first time, you sample the second, you keep on sampling, and then so the average of we assume that the average value of the attributed of the attributes obtained by those samples is equal to the true population, is equal to the true population value. So you sample various samples, then when you get the average of the different samples that you have. And so we assume that the result that you'll get, it will be equal to the true population value. So we talked about the 95%, so implying that you are confident that 95% out of the 100 samples will be able to represent the true population value within the range of precision, which we said, which has a plus or -5. Then with the degree of variability, here we're referring to the distribution of attributes in the population. And so what is most important here is that the more heterogeneous the population is, the larger the sample would be, because by the end of the day, you're going to get different elements with various characteristics. And then the opposite is true. In case it is less homogeneous, then it implies that you require a small sample. Okay, what are the different strategies of determining a sample size? Right, now that we've looked at the factors that determining the sample size, the things that you have to have at the back of your mind, such that you are able to get a sample size that can enable you achieve your objectives. So with the different strategies, of course, when you check in literature, there's a lot of information that you can base on. Sometimes you can use a census for a small population. You can use you can consider basing on literature, implying similar studies that have been done. You can also use published data. Okay, and there are also published tables that are available when they're talking about the sample size. And still, like I mentioned earlier, in case you're quoting a certain sample size, for example, from Yemen 1967, it is always important that you back up your information. If you've not calculated it, and in case you've not based on the different formulas and you're using the published data, then it's also important that you quote that particular author. Okay, I've also talked about use of formulas. You can use a formula in case we've already seen one. If you want to determine a sample size, we've got the Cohen, the Yemen, and also there are formulas for sample size, for mean, and also proportions. But the mostly common used formulas, even if you Google right now on internet, is the Cohen and then the Yemen formulas. So you don't need to cram them. All you need to know, how do I use this particular formula and which one is appropriate? So in case you're considering a sample size for mean or a proportion, for the case of Yemen's, the N is equal to the Z squared. We get the Z value at 95% confidence interval. We've got the variance, that is sigma squared, and then the margin of error. So in case, remember what we said, in case you've got the estimate, the moment you have the estimate, then it will be easy for you to be able to go ahead and determine the sample size. So this is the Yemen formula I quoted, and also the page where you can pick that. So what about in case you're dealing with the sample size for the case of proportions? There is a question here. What proportion of women had skilled birth attendants during their last delivery? What is happening? The proportion, the true population value, we are having it is 60. But now, in case we go further to try to calculate the estimated value, we want to find out, because we are not so certain whether we will be able to get the true population value or the true value. So in that particular case, we can put an allowable acceptable error. So depending, but still, as we know that we need to ensure that we keep it as small as possible, so that the plus and minus difference between the true value and the estimated is what we call the margin of error. So the smaller the margin of error, the more we trust the value that we have. For example, if you consider this slide here, the margin of error, that is the distance between 60 and 40, and then 60 and 80. I mean, that is very big, okay? 20, that is 20%, that is too much. So, but the point is that the smaller the margin of error, the more we trust the value that we've come up with. For example, in this particular case, we are trying to, from the figure, we are seeing that in case I call it D, the margin of error, it is at just 5%. So still we are continuing. I've got my true value. The population is telling me it is 60. And then the estimated value. Remember, the estimated value is picked from the sample size. We are trying to see, does the estimated value picked from the sample correspond to the true value from the population? I've got my D as the margin of error, and then I've got 60 and the estimated value as P from the sample. So the point is, we want to, what do we want to get? We want a sample size to ensure that whatever value that we estimate, in this particular case, say P, okay, from the sample will correspond to the population parameter. That is the true value, capital P. But since I say that you have no guarantee that it will really be exact, so it implies that we put an allowable some level of an error, which I'm calling D. Though still, it is also important that the error level is limited to a certain extent, and it has to be as small as possible. It shouldn't exceed a specified limit that you're talking about. So those are just more details. I talked about the confidence interval. And then when we're starting, we looked at this particular formula and we saw how we can steal from the margin of error, how we can calculate N, provided the true population, provided we know the population estimate, then we can go ahead and calculate N. Okay, so this is what we had in the previous slides, and we saw that all of this is called the margin of error. That is my D. We have the estimate plus or minus the margin of error. Then from this we can make N the subject, and whatever that in case you solve it, whatever that you come up with, you are able to get your N. There is an example. We know that Z, that is the Z value, which is at 95%. We can D, that is a margin of error. We can put it there, and then P, those are the proportions or the probabilities that you want to use. You just need to feed in and then come up with your answer. So in this particular case, using this method, in case you feed in, if your P is equal to 0.4, then the minus, the other fraction will be 0.6, and then your N will be 92.2, which you can approximate to 93. The same story that applies here. So most of the time, what happens is that, always the sample size requirement is highest when our P is equal to 0.5. So implying that if you get a sample of 0.5, so that is 50% of the population. It's a common practice to take P as 0.5 when no information is available, in case you want to estimate the sample size. So in case you do that, if you consider your P as 0.5, then taking your the margin of error as 5%, then if still you feed in, if you put back in this particular formula that we are having here, then we are able to come up with our sample size as 400. We are going to go into more details using R and see how we can come up with that. Other factors that influence some of the calculations that we are going to do in R, we need to understand the desired level of significance, that is our alpha, the probability value, and then the desired power, okay, which is 1 minus beta. Like I said, I've already mentioned that a lot depends on the previous data that is available, as well as the software or the formula that is being used. But we are going to go further and see, remember, when it comes to hypothesis testing, all right, everything still drives into this. With the level of significance, that is our alpha, we need to, what level of alpha are you going to use? And then the desired power, the 1 minus beta. So in that case, what are we going to have? So it is important to note that in case you want to increase the margin, if increasing the margin of error, remember it's from the formula that we've been using. Since it's in the denominator, it implies that increasing the margin of error automatically will reduce the sample size. But in case you want as a big sample size, I mean, when you're trying to calculate out with the known formulas, it is always good to ensure that your margin of error is very small, and then you'll come up with an increase in the sample size. These are just formulas that you can get on internet that can support you in case you want to calculate your sample size. I've already talked about the p-value, that is the probability of obtaining an effect as an extreme or more than what is observed by chance. We have the significance level, that is our alpha. Most of the time, we pick it at 5%, okay? That is the probability of our null hypothesis. And then the power of the test, that is 1 beta, 1 minus beta. So in this particular case, if you remember the hypothesis technique, you collect or reject the null hypothesis when indeed it's what? When indeed it's true. That is the power of the test. And what is important also, we need to determine the effect size. It is when we move on to determine our sample size. So how do you determine the effect size? What we do, we get the difference between the two means, or that those are the samples. We have two independent samples, so we get the difference between the two means or the two samples, and then we divide by the what? The common error variance. And in this particular case here, it is when you take the square root of the variance, you come up with the standard deviation. But like I mentioned earlier, like when you check in literature, a lot of this information is already there, okay? For example, when you check in, Cohen suggests that the effective size of values of 0.2, 0.5, and 0.8, 0.2 represents a small, then 0.5, that is a medium, and then a 0.8, a large effect size, respectively. So you can also read further on that. So we are going to, so what we need to keep at the back of our mind, how do you calculate the effective size in case you've got two independent samples? You need the mean for each, and then later you get the difference and you divide by the standard deviation, all right? What about in case you only have one group? So we are going to see how does that happen. Then the other thing is about, I've talked about the power estimation, the 1 minus beta. Okay, and this one, what happens is that it allows us to determine the sample size we require to detect an effect on a given sample size. But like in hypothesis testing, when it comes to the power of the test, we are looking at the probability of rejecting the null hypothesis if it is false. And so the four quantities that are very important in this relationship when you want to determine the sample size, you need one, the effective size. You need to know the significance level, that is the probability of committing a type 1 error. You need to find out if there is an effect, and then the power, which is equal to 1 minus beta, which is the type 2 error. Okay, still under the hypothesis concept. So the point is that in case you have the effect size, you have the significance level, you have the power. Like most of the time, the power is 80%. Like I mentioned earlier, 80% is one of the recommended power that you can use. Okay, and you can still back that up with literature and using Cohen or Yemen. So these are the four things that you need. In case you've got the effect size, you have the significance level, and then the power, you can automatically determine the sample size. And in case you've got the sample size, the effect size, and then the significance level, you can be able to determine the power. These three things can be used interchangeably, as we will see using various approaches. So this is already given data that we have for the level of significance, that is alpha with the different values, the 1%, the 5%, and then the 10%. We commonly use the 5%. And then the power, the power is the commonly one used is the 80%, but you can go up to 99%. Within R, you can be able to determine the sample size using the PWR package. Okay, we are going to use the PWR package, and this one has got all the basic functions that we need in case we want to calculate our sample size. Of course, as a package, there are many other things that you can read about. For example, Cohon ES, this is the conversion effect size. Already, these are inbuilt functions. All you need to do is to understand when do I use the different functions to support me get the required sample size. So we have the PWR package that we are going to use. That is if you're looking at the basic function for power analysis. And then we have the PW.2P test. You're calculating having different samples. We have the one of chi-square, ANOVA, among others. So still there is more info on that. All this information is within R. Remember, with R we have there is a help command. So in case you type question mark on a certain line in the R Studio, it can support you to give you more details on how to use a certain command. So I think we need the next slides are showing us how we can do it in R. So we are going to use two approaches. One, in case you can do it automatically without any package, but you can still do it in R. And then also, how about in case you're going to use the PW package? So what we are going to do, we are going to use this command power.t.test, and then our n, that is the sample size we want to calculate. Remember, our delta, this is the difference between the two sample means, the groups that we are having. Most of the time, by default, the standard deviation is 1. The significance level, we've talked about it, alpha, which is 0.05. The power, this is my power test, is equal to null, implying that you can specify it to what degree do you want, okay? Are you going to consider 80? Are you going to consider 90? And so on. Then with the type, these are arguments within the command that you can use. You can use them, or you can pick what you want to use and then remove the rest. And then the type, you can also indicate the type. Is it a 2 sample? Is it a 1 sample? Or is it a paired sample? Do you want to use it with the alternative? That is what you're testing. Is it a 2-sided, or you want it to be 1-sided? etc. So I think we can move on to R and then do more practice. The rest of other things you can read. It's just the end of that. Okay. Let me ask in the chat. Let me check. Please give us rest time. Would you like how to show you? So can I? All right, continue and finish. Oh. Can I give a break or continue? I give a break. 10. 15. Okay. We are going to, how do you determine an effect size? Remember, we say to get an effective size, you get, in case it's you're considering the 2 independent samples, you get the mean for 1 sample. In case it's, okay, let's call it group 1, and then you get the mean for group 2. So you get the difference between the 2 independent samples, you divide by the standard deviation. And in that particular case, you'll be able to get the effective size. Beatrice is asking, is Z always 1.96? Well, it is not a must that it has to be 1.96, though most of the literature that you're gonna see, that 1.96 is based on the 95% confidence interval that that we are using. So, but depending on the study that you're doing, for example, in case you're dealing with humans, it could be the 5% allowable error is very big. And so you can move on and say that, no, let me consider, for example, maybe 2% or 3%, but it's not a must. It goes back to what exactly do you want? But in most cases, most of the literature or most of the studies that we do, we consider it to be 95%, which is one, when you take the Z values, 1.96. Okay, Mwanda's answer that it depends on the data, great. Also, Charles is saying that depends on the confidence interval, wonderful. Then Munyang is saying that it is for Z at great at 0.5%. Then 50% seems possible because you don't want to be biased. Yes, you're looking at 50%, half of the population. Maybe half of it we are saying that yes, we vote for so and so. Then the other half is saying that we are not. So half sure, and then the other half not sure. Always in the middle before you draw conclusion. I was reading something and disappeared. Okay, so that your decision will not be skewed to one direction. Yes, read me note 11. I agree with you. That is also okay in case you come up with that conclusion. How do you calculate the power of the conducted study? So like I mentioned earlier, when you're looking at power, this is a 1 minus beta. That is our type 2. That is our type 2 error. Most of the time, for example, in case you're going to use R, all the things are inbuilt. And the recommended P, it's 80% and above. But you have to, depending on the study that you're doing, you can decide to ask yourself to what degree. Remember, with the power, what we are dealing with, you're looking at failing to reject, you accepting the null hypothesis when it is what? When it is false. So the point is that all these things still are driven back to the different hypotheses that you have to put in place. Also the part of the what? Also the part of the alpha. So with R, you can, we are going to see in case what power should I consider. However much, like we say, that you can use literature to sometimes to back up the information that you're having. They're saying 80. But I mean, what about in case maybe you're going to consider, Cohen recommends 80%, maybe you can consider, for, let's say 90 or 95. It all depends. But effect size is usually, how do you get the margin error for the survey? Well, when you're considering for example, in case you're taking, remember we said that when you're considering a sample population and you want to pick an estimate, so it implies that you can pick different samples, and then later by the end of the day, you are able to come up with the average, all the sample, all the estimated parameter, which you think that it will be able to give you a clear representation, or it will correspond to the population value. So in case we are trying to see that the margin of error is as small as possible. So looking at the percentage, in case you consider it, for example, to be 10%, that is really a big difference between from the true value to the estimated value. So you can back that up from literature by using the 5% plus or minus 5%, such that you are not so, because we are saying that even if you go into sampling, there is a certain degree of error that will be involved, and you cannot be so certain that the estimated value that you're going to get will be exactly the population value. So that bit of allowing a sampling error will always take place. Okay. In case of soil sampling, how do I determine the number to collect? So soil samplers, please. Okay, if your H naught is that and greater, it is one-sided Z value. Yes, so I think it's Priscilla. Is it Priska? I agree. You're saying that in case you're considering your null hypothesis to be, and you're having a directional sign like less or greater, you can choose to use a one-sided Z value. And all those values can be picked from the tables. So, Mwanda, whenever you have an equal sign, okay, she was, I think, answering Priska. That is okay. Thank you so much. Okay. Those are some of the questions in the chat. The value of E 5%, why not 6%? That is the margin of error. I think I've explained that. A snowballing sampling method using sampling of households for an interview of certain areas. I also answered that. We are looking at then what is the difference between cluster versus stratified? We said when we are looking at stratified sampling, what we do, we partition our sample into groups. But these groups the partition should be mutually exclusive. And we say, for example, in case you take gender and you're partitioning gender into two groups, the males and then the female, and the issue of homogeneity has to be there within each strata, but heterogeneity has to exist between the strata. So that is with the case of stratified. And then with the cluster, what we are saying that we are looking at the group of the population elements. The word cluster also can mean a grouping, but what happens in this particular case, we take a whole group. We don't pick specific elements within a population that is being sampled. Okay. What if the population size is not defined, that is unknown? How do you estimate and take any sample size you deem appropriate? Remember, for you to determine the sample size, everything starts from you have to pick the appropriate approach. For example, in case you've got a sampling framework or a sampling list, in that particular case, it will be easy for you to come up with, for you to use a systematic sampling approach. Let's take an example. Maybe you're looking at performance of students, okay, in a certain class. You can pick a registration list where those names are, okay. So you'll be able to tell that my N is equal to, within this class is equal to maybe, okay, let's say maybe 100, right? So in that particular case, and then you ask yourself, what N do I want? So you can apply the systematic sampling. But now in other instances whereby you do not know N, then it implies that the approach of the systematic approach might not work for you. But you can consider other cases that we've discussed. Can you go ahead and use maybe consider a simple random sampling? Would you go ahead and first stratify, and then after stratifying, you go ahead and you pick the different elements that you want to include in your sample, such that you come up with a required number? It all goes back to that. Can confidence interval and level of precision be used interchangeably? I think here the point is to understand what confidence level is and what the level of precision is. Okay, the moment you understand what the two means and the confidence interval, we are looking at the degree of risk. At what confidence can we stand and say that our estimate lies between, we can be confident and say that our true estimate lies between plus or minus 5. Maybe what might be confusing is that most of the time, whereby we choose our confidence level to be 95%. 95% implying that from the different samples that you're going to pick, it implies that at least 95 of the samples out of 100 will represent the true population, and you're only giving allowance, say, of only the 5%. But at least with the many samples you're going to pick, the 95 will give you a true representation for the population size. Okay, and the level of precision, maybe if that word is hard for you, what should put at the back of your mind is just the margin of error or the sampling error that you can use. So like I mentioned, most of the time we have plus or minus 5, but however it can reduce either to 3, plus or minus 3, or plus or minus 2. And different textbooks or different literature have got a different level of precision depending on the kind of study that you are doing and what you want to achieve. Okay. I've answered is Z always 1.96. Suppose you don't have proportions, but you're dealing with a finite population. How do you calculate the sample size? Okay, so we've looked at different methods. If you remember, there is a colleague who stated that in this particular case you don't have the proportion, you can consider your P to be equal to 50%. That is 0. You're not so certain of which probability or proportion it will take, but at least what you can use a 50 and 50%, implying that maybe if you're using a binary output, it will tell you maybe the 50 fall into the sample, the 50 do not. So in that particular case, in case you consider your P to be 50%, then you will be able to calculate your sample size. I think I explained that in one of the slides, and you can come up with your sample size. Okay, some break, it's all right. I'm going to give a break of 15 minutes. So we are returning at what time? Huh? No, I was answering questions. 43. Okay, let's resume at 12:43. Okay. So let's resume at 12:45, and then we'll go directly into R and see how do we determine the sample size. 12:45. Isn't it a lot? Hmm? Oh. Hey, welcome back. It's 12:45. Hope you had a good break. And by the time we break off, I'd answered some of the questions that were posted in the chat and then in the Q&A. So when you check in Dev 4 material, there is an R script that is called sample size underscore power.r. So right now, I want you to open this script such that we follow through the commands and see how we can determine the sample size. Open the R script in Dev 4 and we continue. Maybe the other thing that I would like you to do is to install package PWR, because we are not going to, it's what we are going to use. I understand among the different packages that you've been installing, the PW package, the power analysis package in R is not there. So can you install the PWR such that as we proceed, we'll use it as we go through the R script. Install PWR package. Remember, when you're installing, we use the install.packages command. Then after, the moment we successfully install, we load it, we load the PWR, because we need some of the inbuilt functions in that package that we are going to use when we are computing N. So let me check in the chat. Have you been able to install PWR package? Okay, Mona is saying done. There's only one person, Wycliffe, yes. Adam, okay. Andrew, yes. Please install. After installing, then load it. After installing, use library, then in bracket you put PWR, such that you load it. Unless if you don't load it, you get errors. So we need it on your computer. Okay, so can I continue? After installing, load. You're done? Type in the chat. Can I continue? All right. Okay. All right. Okay, let's continue. So here we've got two techniques that we are going to use. One, without installing any package, and then what about in case we need the functions that are inside the PWR? We're going to see that later. But let's first proceed. Let's first start with the first example where we want to use the power.t.test. There are various options that you can use, but right now I want us to use the power.t.test command. In here, what we are going to do, we are going to specify the power value. Most of the time, it's 80% is recommended, but you can put 80 and above, and then we want to see what else do I need to include there. But like I said, R has got a help window in case you're not so sure of how a certain command works. It is always better to ask, such that you read about the description, you read about the usage, and you also get to know about the different arguments that are within the command that you want to use. For example, in case you type power.t.test and then you run, if you run that line and you come and check in your help window, what is going to happen is that we are going to see the description of the test. This one's power calculations for 1 and 2 sample t-tests. All right. So if you read closely, there is a description, and then we have the usage. Okay. You can get N, that is the number of observations per group, what you need. The delta, remember we are looking at the difference in mean sizes. That is my delta, mu1 minus mu2. By default, SD is 1 for R, but you can change that. We've got the standard deviation, that is the type 1 error probability. The level of significance is 0.05, that is the type 1 error probability. Then in case you don't have the power, you can put it, you can indicate the type. Is it a 2 sample, is it a 1 sample, or it is paired, all right? Then it gives you the alternative hypothesis, whether it is 2-sided or 1-sided, and so on. So you can come and read more details about a certain command. And it's quite interesting that also R gives you an example in the end that, how do you approach a certain command and then you apply it to your work. So that is the command we are going to use now. So in case I've got the power.t.test, inside one of the arguments, there is delta, that is the difference between the means. So in case I assume that the difference between the means is 0.2, and then the standard deviation is 0.5, all right? And my power is 0.8. This is just by default. I'm just getting an example. So in case I run this line, inside here, if you check the different arguments inside the power.t.test, I've not indicated the type as per what we saw in the help command. But in case you want to indicate the type, whether it's a 1 sample or a 2 sample, but most of the time by default, it gives you a 2 sample. So in case you run this line, when you run that line and then check your output in the R console, what happens is that it is telling you by default, it will give you a 2 sample test. That all you need to do in this particular case, it gives you that you will need 99, n as your 99. Because remember, and these formulas, all the commands that are inbuilt in R, they are based on Cohen or Yemen's formula. Already the existing formulas. So the point is knowing how to apply them and get the required n. So my delta is 0.2. If you've got delta 0.2, the SB at 0.5, and your power at 0.9 with the alternative hypothesis of 2-sided. So it implies that the n, in this particular case, n is the number that you need in each group. In this particular case, which is going to be 99. So the total that you need is going to be 99 times 2, but in each particular group, you'll have 99. In this first line, it is equivalent to the second line, but only that in this case, I've stated the type, which is a 2 sample test, but by default, R gives that. So I'm going to skip that. So basing on that, from the conclusion, you can say if the difference in the mean size is 0.2 with a standard deviation of 0.5 and power of 0.8, that is 80%, then the recommended or the recommendable sample size, it's going to be 99 from each independent group. In total, for us to come up with the total that we'll have, so it will be 99 times 2. Okay. We can still do the same using the same command, assuming now I change my power to 90, okay? That is 0.9, and then my delta to 0.3, then standard deviation 0.28. But this time around, I consider a 1 sample. So the aim is I want to compute a sample size that will enable me to achieve a power of 90% in my study, whereby with the aim of having the difference in the means of 0.3 with a standard deviation of 0.2. So all you need to do is to come and feed in these different arguments. And then thereafter that, remember we said it's just 1 sample, and then you run that particular line. So for a case of the 1 sample t-test power calculation, it will tell you if you're considering, if you're taking 90%, all right, with a significance level of 0.05. By default, R knows it is 0.05. but you can adjust. In case you don't include it in the command, it will take the inbuilt one of 0.05. But in case you want to change it, for example, to maybe to 0.1, or you want to change to 99%, then you can as well do that. But basing on this, it's saying that your sample size will be 11, basing on what we feed in here. So that is the part of the power.t.test. All right. Also, remember, what about in case of a two-sample test? I'm using similar argument, but what I'm changing here is the sample size. Okay. My power, again, it's 90%. I want to reach a power of 90% in my study, and the difference in the two sample is 0.3. Those are the difference in the means, with a standard deviation of 0.26. So in case I run that line, what I'm going to come up with, the result is that the recommended N that will suit this kind of information, it's going to be 19 from each sample group, because in this case we are considering two samples. Your N is 0.3, my SD is 0.28, and then my power of 90%. Remember, in this case, we are having our N as 19. What about in case I change to 18? What happens? Will N change? If you check here, in case I put my N to be 0.8, then the degree increases from 11 to 14 to 15 in case I approximate. So implying that from each group, I'll need to take my N as 15. So the total sample will be 15 by 2. Okay, this one, the one I sent, it had 9, so I can put back to that. And then what about in case we are considering a binary response? For example, the example we had whereby in the example about if people were saying that AIDS were a real healthy concern, and 29% said it was, and the 71 said it wasn't. All right. So in such a case, how do we go about that? We are considering proportions of two different groups of people. So we can use a similar example or the same information or the knowledge acquired from there, and then we see how do we apply it here. So what we are going to do, in case you're considering proportions, in this particular case, we are going to use the power.prop.test. This one, the one that I'm highlighting. And within here, in case you need more details, you can use the help window, and it will show you the description, the usage, and the details of the different arguments within a particular command. But the common ones, the common ones, we can have proportion 1, which is equal to 0.2, and then proportion 2 to 0.5. In the previous one, in case I'm to consider what I had earlier, my P was in the statement we had in our slides, we had 29, so it's going to be 0.29, and then the other proportion was 0. So it will be 0.71. So looking at this first one, these are just proportions. So the message is, what N will I need to use such that I have 0.6% of in proportion 1, or in subpopulation 1, and then 0.5 in the other. So in case I run that, what is going to happen? It's telling me that if P1 is 60% and P2, you give it a fraction of 0.5. Also having an alpha of 0.05, considering your power as 0.8, it implies that you will need 387 elements or respondents in each particular group, both in P1 and then in group 1 and then in group 2. So the conclusion that you can make is that in order for you to achieve a power of 80%, assuming that these are the probabilities that you're coming up with, the 0.6 and then the 0.5, then your study should include at least 387 subjects in each group, because here we are dealing with proportions. Of course, like I said, it varies, it will keep changing. And then what about in case I run the second line, what is gonna happen? So it implies that if group 1, I'm using 0.29, and then group 2 is 0.71, then in each group, I'll need 21 individuals or subjects that I will need in each group. Those are the inbuilt commands that we can use. But we can also look at a scenario. What about in case I use the PW package? Remember, after installing, all you need to do is to load the package. Okay, the moment you load the package, then it implies that you can now go ahead and use the different functions that are within that package. Otherwise, if it is not loaded, you're going to encounter a scenario whereby you're getting errors. Okay, so in this case, having loaded the PWR library, so we also want to see how do we get the sample size. In case I'm to consider only one sample, if you remember very well initially, in case you're having one sample, how do you test your sample mean? Most of the time it is x bar minus mu naught, then divide by s over the square root of n. Okay, that is how we find it. So in case it is a 2-sample test, most of the time we get the difference between the means, and then you divide by what? By s root n. So here we are going to use, we are using the same test, but now here what is changing? Initially, in case you look at my console, we are writing the word power, okay? Power in full, power.prop.test. But in case you're applying the PWR package, then all you need to do is to write pwr.t.test, okay? You can as well check in case you want to get more details. You can put a question mark and then ask R, what is this command all about? Okay, and then you can run that. The moment you run, you can come and check in your help window and see how you can, what is involved in that particular command. So I've got N, which I can define, that is the size. Then my D, that is the margin of error. Then the significance level. We've got P, we've got the type, my P, the power is null. You can proceed down and then read through. Here we are told that my N, those are the number of observation per sample, the ones that I will need. Then we've got here the D is the effective size. I think you can see here it is Cohen's D, implying that the formulas that are developed within R, they were based on Cohen's. The difference between the means divided by the pooled standard deviation. We saw that, what the effective size is all about. And then the significance level, the power, and then the type of test that you want, whether it's a 1 or 2. So these are the same arguments that I'm putting on this line here. And first, the difference in the means, that is in case I'm to consider one sample. So it will be the sample mean minus the hypothesized mean. So in case I consider my delta to be equal to 10, and then my significance, my sigma, that is the standard error of the mean, to be 20. So for me to get the effective size, I need to divide. So it's going to be delta over sigma, which will give me the effective size, such that I'm able to, in case I come to my formula, I'm able to feed in this particular D in my command. Remember that these are effective size, and we get the difference between the means and we divide by the standard deviation. So it is what I need at the start, and it's what I'm calling, in this case, my R, which is equal to D. I left my significance level 0.05. The power is 0.9, but it can change. most of it is 80% and above. And in case I'm considering only a one sample size, also remember the trick is that in case you've got the power, automatically you're able to determine the sample size. But it can also be the other way around. In case you've got N, you can be R can be able to give you the estimated power that you can apply. So if I'm to consider a one sample and I run this line, sorry, if you look here, they're telling me that object R not found, implying that I need to first go back and run these particular lines such that the R I'm talking about here, which is delta divided by sigma, can easily, it is captured. So what I do, I run the difference between the means, which is 10, I run my standard error of the mean, and then I come and get what R, how R is being determined. Whatever I'm doing here, it is being recorded in the environment, it's being stored in the environment. So now I'm good to go to ask what will be the recommended N in this particular case, in case my effective size in this particular case is a half, because that is 10 over 20, which is a 1 out of 2. So in case I run this line and I look in my console, it says that in case of a one sample and you're considering your power to be 0.9 and your effective size as 0.5, then the recommended sample size that you need to use is 40. It's 44 in this case, if I'm to round off. So most of the time, the power depends on your objective. And so if your objective is to achieve 95% as the specified power, then for you, the sample size that you choose that R will recommend is 44. Okay, what about in case we are to consider a two sample? What is going to happen? I'm still using the same example, but this time around, I'm changing the level of significance to 0.1. I'm leaving my power to be 0.8, and the type I'm considering a two sample. So in case I run that line, and I look in my console, what it states that basing on a two sample t-test per calculation, I'll have 50 in each group. Okay, I'll have 50 subjects in each group. If my effective size is 0.5, and then my significance level as 0.1. So remember, you can play around with these arguments. You can ask yourself, what if I change instead of 0.5, in case I put, initially it was 0.1, and my N from each sample is 50. What about in case I consider 0.05? What happens? So here we see that in case we will reduce to 0.05, your N increases to 63.7. So roughly it is 64. You need 64 subjects in each group that you're going to consider. So the point is you need to get to know what exactly or what objective do you want to achieve. Like I mentioned earlier, that if you've got the power, you've got your effect size, you can be able to get you. Then if you have those components, it is possible for you to compute for N. But also, in case you've got N, you can be able to get the power. For example, when you come to this particular line, power.prop.test, if my N is equal to 28 in each of the groups, whereby the proportion for the first group is 0.3 and the proportion for the second group is 0.55, then excuse me, then I can be able to calculate here. What is missing is my P, because what is most important, I need the N and then I need the P. But in this scenario, I've got the N. So if I run that line and I check down here, it is telling me that the power will be 0.47 if my N is 28. In other words, the power of the study, which includes 28 subjects in each of the groups, okay, in group 1, which has got the proportion of 0.3, and group 2, which is 0.55, it will be 0.47. So, and then in this last one, it is in case you've got N as 6, you've got a delta, and then the standard deviation. Remember, if you get the delta divided by the standard deviation, we are coming up with the effective size, all right? And so in this case, we want to get the power. I've got my N as 6, and I'm considering a 2 sample. If I run that, it is telling me that in case I'm considering 2 sample groups and my N is 6 in each. So it implies that I'll need a power of 0.9 of 39%. You can, what about, maybe you can say, what if I increase my N, let's say if it is 50, what is going to happen in case I run again? So you see, in case you increase your N, your power is 99. So I mean, you can check, and even if you put in, for example, 80, or if you put in 80%, what is going to happen to your N? And that is how you can determine the sample size. Any question? And not necessarily, it doesn't matter. It depends on what proportion you're picking for 1, and then the proportion you're picking for 2. That is Wycliffe's question. All right, so I think that is the part I wanted to present today on an overview of sample surveys. And I think we've gotten our objective. How can you determine a sample size for your work, so that you're able to calculate, you're able to achieve your objectives. Sorry? Okay. So I'm going to stop here, and then Professor Susan is going to set in with regression. I don't know whether we are covering a lot today, but what I know, the information that we are working on, it's very important. In one or another, you're going to need to apply it in your research. Thank you so much, and thanks for being a good audience. In case of more, yes, in case of more than 2 groups, you use an ANOVA. Like I said, in this particular case, we are just getting just a little of what we are supposed to cover. But you can use the same for ANOVA. You can use the same in case of a chi-square test, and you get more details like what I shared in the PowerPoint. So you can check that, and everything can still be done in R. Okay, all right. I'm going to answer the questions when in the Q&A. I'm going to type in the answers as Professor Susan is continuing. Thank you.
Good afternoon, participants. I hope you are feeling good and you've had a good run with my colleague, Dr. Thomas and Dr. Helen. I believe you've benefited a lot. For those doing surveys, now you can determine the sample size. For those doing experiments, you can determine the number of replicates. Now we want to go into inferential statistics, and we want to look at regression and correlation. So we are first of all going to look at the theory, then tomorrow we can do practicals. Okay, let me share. Okay, hello participants, can you hear me in the chat? You don't need attendance since you're not very many. The attendance is taken automatically from Zoom. They record the attendance. So don't worry about attendance. Okay, thank you very much. So we are now going to change our goalposts. We are assuming now you know how to collect data using experimental design. You know how to collect data using surveys. You know how to design tools. Now, after you've collected data, we've already told you how to do some exploratory data analysis. Now we want to see if, assuming we've found trends in our data, how do we deal with those trends? So today we are going to look at correlation and regression with R. Okay, the other thing is if you need these slides, you can pick them from the Google Drive. We've already sent them in. And I wanted to know whether my slides are clear and they are moving. So let me try to move them a bit. And if they are moving, then we're good to go. They seem not to be moving. Okay. Okay, so I'm going to stop sharing. Give me 1 minute, then I make it more clear. Okay, so let's look at correlation. We find that correlation is a measure of degree of linear association between two variables. It varies between -1 to +1. It is a descriptive statistics for regression. We have positive linear correlation. We also have negative linear correlation and no correlation. So when we have a plot where points are running from bottom left to the top right, then that is a positive linear correlation. And if the points are running from the bottom left to the bottom right, then that is a negative correlation. And if it's just a random scatter of points, then we have no correlation or no linear correlation. Correlation helps us determine the strength of the relationship and direction. By strength, we are talking about the magnitude, while the direction is either positive or negative. Correlation is denoted by a Roman letter small r or lowercase r. We've already said it ranges from -1 to +1. A positive value indicates a positive correlation, while a negative value indicates negative correlation. If correlation is equal to +1, then the data set has perfect positive linear correlation. And if it's -1, it indicates perfect negative correlation, while R equal to 0 would indicate no correlation. Now, in some statistical textbooks, when we want to interpret the values of correlation, some say if R is equal to 0.5, then that is moderate correlation. Anything below 0.5 is weak correlation, while anything above 0.5 is strong correlation irrespective of the direction. So if we have two variables that are continuous, then we use Pearson linear correlation, also denoted as small r, and there is a formula, but you can see I've put a hint. You will not need to compute this by hand in this course. So in case you just want to check whether the correlation produced is correct, then you can use that formula. Now, as a definition of like Sx is the sum of squares for the x data which represents the explanatory variable, and Sy is the sum of squares for the response. Okay, so we have some graphs here. You can see that I was saying that if points range from the negative side to from the left to the bottom right, then that is a positive. You can see the values here, I mean the red points here show a positive correlation, and they also show that is strong because they almost go through the 0 point. The 0 point is right here where the graph originates from. And if we look below that, we find that the points are a bit spread and they are not really going through the 0 point. So that is positive correlation, but it is, you can see it is 0.67. And our random scatter of points, you can see this is almost 0 or no correlation, but there's a correlation of 0.07. So then we have the negative correlation. You can see the points run from the left top corner to the bottom right corner. And because they almost go through this point here, it shows it is a strong negative correlation. While here we find it is negative correlation, but very weak. And this is moderate correlation. So if two variables are correlated, it does not mean that one variable causes the other to change. For example, religion does not cause crime to change. If you find that a data set, you find that most of the, let's say, this is just an example, most of the Protestants are putting on blue shirts in the training, it does not necessarily mean that being a Protestant is associated with blue shirts. Or if Pentecostal are putting on red skirts, does not necessarily mean that being Pentecostal is associated with red skirts. So once two variables are associated, it's just telling us that these two variables are linearly related and their relationship is either strong, weak, or moderate, but one does not cause the other to change. So Pearson correlation measures strength and direction of relationship between two variables, and the variables have to be continuous. If variables are not continuous, for example, ordinal data, then we calculate Spearman's correlation. Okay. In R, we use a function called in bracket the variables to compute the correlation coefficient. And if we want to test the association between the two variables, then we use co.test. Okay. So co.test gives you both the correlation value or correlation coefficient and the p-value. So in R, you can also specify the method. For example, if X and Y are our variables and want to know the correlation, then we use co-XY method is equal to either Pearson, Kendall, or Spearman's correlation. So you can actually change the method depending on the type of data that you have. Here there's a note that XY, the numerical vectors have to have same length for you to use the correlation method in R. We have a plot here. In case you want to construct a plot in R, we can use the Gigi scatter plot command to construct a plot, and it also produces the correlation value and the corresponding p-value. So if you see in your notes, you can see a correlation value up here on top of 0.92, meaning that price is highly or strongly correlated with weight, and the correlation is positive. You find that the p-value is 2.2 times 10 to the power minus 16. And this p-value is testing the hypothesis that the correlation between price and weight, the null hypothesis is that there's no correlation between price and weight at a probability of 0.05. Then the alternative is that there is correlation between price and weight. Now, if we get a p-value as smaller than 0.05, then we have evidence to reject the null and conclude that price is positively and strongly correlated with weight according to the results we have. So the correlation value is 0.92. It is positive and strong, meaning price is strongly correlated with weight, but also the correlation is significantly different from 0. Okay, so for you to obtain a correlation value in R, we said we use core.test. Then as is an object, so we can name our value as, or we can name that command line with an object as, so that we get our results. So once you run that command line, then you're able now to get as, and you print it out. The printout looks like this. It has Pearson's product moment correlation. It shows the data. We were getting correlation between weight and price. The t-value is 24.04, 24.033 degrees of freedom, the p-value, and then it says alternative hypothesis, true correlation is not equal to 0. And then it also gives you the confidence interval for the correlation value and the correlation value itself, which is 0.9246. So that's what we'll get in R. And the next slide tells us how to interpret the output. We get a t-value of 24.033 on 98 degrees of freedom, with our p-value of 2.2 times 10 to the power minus 16, and the confidence interval. The p-value of the test is less than alpha. Alpha is the significance level that researchers set for their tests. And it is the probability, the smallest probability for the null hypothesis to be assumed to be right. So anything below 0.05 shows that there is evidence to reject the null. And here our null is that the correlation between price and weight is equal to 0. And because the value is greater than 0, that's why even the corresponding p-value is smaller than 0.05, showing us that there is evidence to reject the null and conclude that weight and price are significantly correlated with our correlation value of 0.92. Okay. So we can also produce a correlation matrix between many variables. So in case you have more than 2 variables, you can produce a correlation matrix. And in order to do that, we need to install a package called HMISC HIMSS package. And then we use rco function to produce a correlation matrix. As we shall see, we've already used that in our exploratory data analysis. Now, if a pair, okay, before I go into regression, let me check in the chat. Okay, is there any question? Should I continue with the regression? Any question? Or I continue? Okay. Okay, no question. And we have at least 30 minutes to go. I said Spearman is used when you have ordinal data or ranks. We need material. The material is in the Google Drive. Go under day 5. I thought that we wouldn't be able to cover this today, but we've started with day 4. So go into day 5 and download the material. And there are also data sets that we are going to use tomorrow. Okay, my colleague has also posted the Google Drive, so you can go there and pick the slides we are using now. Okay. If a pair of variables has a significant linear correlation, then the relationship between the two data values can be roughly approximated by a linear equation. The process of finding a linear equation which best suits the data is called linear regression. And the line of best fit, which we are going to see, is called a regression line. So regression analysis is a study of the relationship between variables with the objective of identifying the relationship, whether it's linear or not, estimating the parameters, which include the intercept and the slope, and validating the relationship. By validating the relationship, we are looking at the assumptions. Under linear regression, there are some assumptions which we are going to see. And for our model to be valid, those assumptions should not be violated. We know that from simple mathematics, linear relationship is a straight line model, which consists of the response y and has an intercept beta naught and a slope beta 1 plus x, where a should be the slope, and it shows for each unit increment in x, y increases by the change b. And b naught is the intercept. And when x is equal to 0, y is equal to the value of the intercept. Okay. So slope is represented by b1 and describes the change in y for every unit change in x. The y-intercept is represented by b naught and is the predicted value for the response when x is equal to 0. The line of best fit, which we'll see later, gives the predicted value y hat at any given value of x. Each observation will not fall exactly on the line of best fit, and the difference between the observed value, the response, and the predicted value from the line of best fit is known as the residue, which is denoted as E or epsilon. So the difference between the response that you collect from the field and the value obtained by the line of best fit, y hat, is epsilon. The line of best fit minimizes the sum of the squared error terms obtained by the method of least square. So for us to obtain the line of best fit, we use a method of least square called LOS. Under LOS, the slope and intercept are called least square estimates. Okay. So the regression line obtained by LOS is y hat is equal to beta 1 x plus b naught. This straight line you see does not go through all the red points. You see the red points is the observed data, and the blue line is the regression line. It does not touch all the red points. And the difference between the blue line and the red point is what we call the residual. So I've just said that notice that the regression line does not go through every point. Using the ordinary square regression model tries to balance the difference between the straight line model and the observed data points, which is called our line of best fit. The residual is the difference between the red points and the blue line. The red points are the observed values, and the blue line is the predicted value. So observed minus predicted is equal to residual. So here is a data set which I obtained from an open source called SUNY ESF. We find that the blue line is the model line or the fitted line or the regression line. The red points are the observed value. And if we stretch out one point, you will see in your diagram that from the blue line to this red point, the observed value, there is a difference. And that difference is what we call residual or error. And the blue line is called the model line. When we use the model line to predict y for a given value of x, we get the predicted value. So the method of ordinary square regression minimizes the sum of square differences between the observed and predicted value. So if we square our residuals and then differentiate that particular equation, we are able now to come up with equations to compute our slope and intercept. So we are not going to go into the math, but I just want to mention in passing that our slope and intercept is obtained from the deviations, the residuals, the deviations between the observed and the predicted value. Okay. So we've already said that the slope and intercept are parameters that are obtained by least square method or LOS, and they are called least square estimates. So from the straight line model, the least square principle involves the determination of this intercept and the slope to minimize the vertical distance between the observed and the fitted value. So I say that once we get the difference between the observed and the predicted value, we differentiate with respect to the intercept and slope, and we are able to come up with these equations you see. You can see beta naught is the intercept and is equal to the mean of the response minus the slope and the mean of the predicted value. Then the slope is equal to the sum of the square of the products of y and x over the sums of squares for x. I have expanded the sums of squares for the cross product and also sums of squares for x. So this is how it is expanded in case you want to know. So in other ways, so this is one way of determining the slope and intercept. You can also use this method to determine the slope and the intercept. Okay, and the expansion is here. So in case you want to go in details of how they obtain those values manually, those are the formulas we can use. We said residuals are deviations of observed and predicted values. They are denoted with small letter e or epsilon. And you can see that for each observed value, we can compute an epsilon. So here we have E3, E2, E1, the difference between the first observed value and the fitted line. So residuals are useful. They allow us to calculate the sum of squares. The error sums of squares is what we use to test whether there is a linear association between y and x, or the response and the predicted value. So this is the formula for computing the error sums of squares. We shall see this later. And in turn, we can now compute the variance of the data set. So the variance of the data set is the sums of squares error over the degrees of freedom, which is n minus 2. N minus 2 comes from two parameters, the intercept and the slope. Now we can also compute the coefficient of determination, okay, using our error sums of squares over the total variation. So 1 minus the ratio of error sums of squares over the total sums of squares gives us our R squared, which is the coefficient of determination. Okay. R squared coefficient of determination tells us the proportion of variability in the response explained by the model. So when we conduct our regression, we are able to know how much variability has been explained in the response. When we collect our data, the response has 100% variability due to either the variables we've collected or other factors in the environment or in the experimental setting. So the amount of variability R squared is 1 minus the regression sums of squares over the total sums of squares. Okay. Okay. So how do we use R squared? When we are comparing different models, we need to know how much proportion of variability is explained by the regression model. So if you have more than 2 models, we can use our R squared to compare how well the models fit our data. So when R squared is equal to 0, it means no variation has been explained by the regression model. If you have R squared of 0.8549, that means that 85.4% has been explained by the regression model, the response, or the variability explained in the response by the model is 85%. So the parameter of interest under regression is the slope. When there is no slope, then we have a straight line. When there is a slope, then we need to know, is the slope different from 0 or not equal to 0? The statistical hypothesis under regression, the null is that the slope is equal to 0, meaning no linear relationship between the response and the independent variable. And the alternative is that the slope is not equal to 0, meaning there is a linear relationship between the response and the independent variable. Now, how do we determine, given our data set, how do we determine the response and the independent variable? Most cases, the independent variable is measured with minimal error. For example, if we are looking at diameter and biomass, biomass is a function of diameter and sometimes height. And some cases we find that biomass is a function of diameter and crown width of the trees. So you find that biomass varies a lot, not only due to diameter and height, but also other environmental factors. So it qualifies to be a response. While diameter is measured with minimal error, the error can be only introduced by the person measuring with a slide caliper or the tape measure. So that's how you determine the independent variable and the response. So if you're given a data set and you're given an objective, you'll be able to know which one is the response from the objective and also from the data set. How do we test this hypothesis? We can use a t-test and a regression, whereby we are testing that the slope minus 0 over the standard error of the slope. And that particular t-test follows degrees of freedom n minus 2. We said 2 comes from 2 parameters, the intercept and the slope. Okay. So before we go into the assumptions, I wanted us to look at, maybe let me just mention in passing the assumptions and also check whether we still have time. We have 13 minutes, okay. So under regression, we have some assumptions. We assume that the response is a random variable, normally distributed with mean mu and variance sigma squared. We also assume that the unknown random errors, which I'm calling residuals, are assumed to be independent, meaning they are not correlated, normally distributed with mean 0 and constant variance sigma squared. We also assume that the response is linearly related to the independent variables. So those are the assumptions. We are going to look at that in details, those assumptions later on. Now, under regression, we also have what we call an analysis of variance table. The analysis of variance table shows us that the total variation in the response is divided into the regression sums of squares and the residue. So the total sums of squares is denoted as SY in some textbooks or SSY, which means sums of squares of Y, which is expanded as the difference between the observed value of Y and the mean of Y squared. So we sum all those deviations and get the total variation. Then we have what we call the regression variation. After we've regressed onto X, we get what we call the regression or explained deviations. Okay. Then we have the sums of squares due to error or residual or unexplained variation. So the total variation in the response is divided into the regression variation or the variation explained by regression model and the unexplained variation, which is SSE. Okay, in the chat, any question? Any questions so far? Oh, okay. Thank you. My colleague has already answered most of the question. Difference between correlation and regression. Somebody says, can you repeat from the beginning? I don't know. Okay, so we'll look at the analysis of variance table in details. Correlation, I believe you wanted to know the difference between correlation and regression. Correlation is a measure of linear association between the response and the independent variable, and it only shows the direction and magnitude. Meanwhile, regression, we are able to identify the relationship, whether it's linear or nonlinear, etc. And then we are able to estimate the parameters, the slope and intercept, and we are able to validate the regression model or the assumptions under the regression model. Okay. So this is the analysis of variance table we are talking about. Under the analysis of variance table, we have source of variation and we have regression. Then we have the residual or error, which is the residual due to other factors not included in the model. So the regression here, regression variation, it is the amount of variability explained by the model. And whatever remains, we call it residual. Then we have the total variation. Now let's concentrate on the degrees of freedom. We see that this is a regression between volume and diameter. The number of parameters we have are only two, the intercept and the slope. The degrees of freedom associated with the regression is either equal to the number of independent variables in the model, or it is equal to the number of parameters minus 1. So I have just said that in this model of volume and diameter, we only have the intercept and slope. So if we subtract 1, we get 1. And if we use the other formula that degrees of freedom for regression is equal to the number of independent variables in the model, that means that the regression degrees of freedom is equal to 1 because our independent variable is 1 only. Okay. Then when we go to the residual degrees of freedom or error degrees of freedom, the error degrees of freedom is equal to the number of observed values minus the number of parameters. We've just said we have only 2 parameters. So the total number of observations minus 2 gives us the residual degrees of freedom. Then the total degrees of freedom is the total number of observations minus 1. So if we have our degrees of freedom for total at 30, then our number of observations is equal to 30, is 30 plus 1, which gives us 31 observations. So you can use the formula n minus 1 is equal to 30, then n will equal to 30 plus 1, giving us 31 observations. And then the residual degrees of freedom will be 31 minus 2 gives us 29 degrees of freedom. Sums of squares for regression, we can compute that, and there are formulas. And also error sums of squares is the total sums of squares minus the regression sums of squares. We saw the formula for total sums of squares, which is the SY. It's the sums of squares difference between the response and the mean of the response squared. Mean square MS is mean square. From the table you see, it is the ratio of sums of square, which is SS, and degrees of freedom. So if we get for regression, the mean square here is equal to the sums of squares, which is 7,581.8 divided by 1. gives us the mean square. And also for residual, it is 524.3 divided by 29 gives us 18. The F value is the ratio of mean square regression and mean square error or residual, gives us the F value. Then the P value, we use the principles of probability to calculate it. So if you know probability, you can calculate the probability of F is equal to 419, then you calculate using the F distribution table. Okay, so when we analyze our data, we get what we call S. S is the standard deviation of the data set, which is the square root of 18.1. So in our table, we have 18.1 as the mean square error. So the square root of mean square error gives us S. So you can try out if you have a calculator, 18.1, get its square root gives you 4.252. R squared, we talked about its coefficient of determination. It shows us the proportion of variability explained in volume by the regression model. R squared adjusts, the interpretation is the same, it's the amount of variability explained in volume by the regression model, but it adjusts for any parameter added in the model. So in the regression model, if we add the intercept and slope, then R squared is adjusted. That's why you see those two values are different. We use R squared adjust when we are looking at multiple regression. Okay. Okay, so I think we have 3 minutes. And I presume you're exhausted after giving you a lot of information. We will continue from here tomorrow and also do some practical. So since you have the script with you and you have the data, try out the practical and see whether you can attempt to do regression without even my intervention. Thank you very much for being patient with us. We've given you a lot of information. Please revise, practice,